you, Nirban Chatterjee, sir. This is Santosh here, and welcome to this course on AI and ML. This is, I think, the third day. Mm, today's session, I will be discussing some of the techniques in machine learning. I mean, hands-on. I will be providing you some Python code to implement how to implement some of the regression techniques in the first part of my session. In the next part of the session, after the break, I will be explaining you about exploratory data analysis and different univariate, multivariate, PDF and histograms and CDF analysis. So we'll discuss about that. So the outline of my session will be like that. First, we'll be discussing about various regression techniques. I mean, so already we know that regression techniques comes under supervised machine learning algorithms, right? So everyone knows that what is machine learning, and there are mainly two types of machine learning algorithms: supervised and unsupervised. So in supervised, we know that for every data we have a label is assigned, and for unsupervised there won't be a label. So depending upon the label, we'll train the model and we'll split the data into test and train set, and we'll train our model with the training set, and we'll test with the testing set, right? So here in one of the major algorithms we see in machine learning are the regression and classification algorithms. So in the first of my session, I will be discussing some of the regression algorithms, like I will be discussing like linear regression. Next, I will be discussing polynomial regression. Next, I will be discussing about multiple linear regression, MLR, multiple linear regression. Okay, so normally these regression techniques will used for, to predict some future events. Like I will give some examples. For example, if I have a data set like X and Y, I have two data points. Say, if I have a X data point saying the age of the car, it's mentioning the age of the car. If the age of the car is 2 years, I know that the speed with which it will go, it's say 90 kilometers per hour. Like that, have some points, like if age of the car is 3 years, it's go with 85 kilometers. If age of the car is 5, it go with 92. And like that, I have some data. For example, 85, and if the age of the car is 10, it is 92, and so on. Like this, I have this much number of points. And say if I want to predict what is the speed of the car, if its age is, for example, 6, it is not given, right? So what could be the value? We can predict using some regression techniques like linear regression. So this is some simple example. Later we'll go with the polynomial linear regression, polynomial regression, and we'll discuss about the MLR. So first we discuss about the linear regression now. So what I will be doing is I will be giving some mathematical institution. Not into the, total mathematically. Mostly I will be showing you the code part. There are some libraries in Python by which we can implement this all three methods: linear regression, polynomial regression, and multiple linear regression. We can implement all this through some libraries already there in your Python. Okay, so we use these libraries to implement all these algorithms. I will show you the code, and everything the code I will be doing will be in Google Colab. So how many of you are aware of Google Colab? uh, So, have you? Anyone has used Google
Never.
Colab?
No, sir, I haven't.
Okay, no problem. So the people have not used Google Colab. So Google Colab is a open source, cloud platform for doing machine learning task. They provide IPython notebooks, free IPython notebooks. Just like you do Python code in any of the platforms like Jupyter, like that, right? Spider, like that. So you here Google Colab gives you IPython notebooks. So I will show you how Google Colabs looks like. So in order to create a Google Colab account, only thing you have to have a Google Gmail ID, gmail.com ID. If you have a Gmail ID, and you should be, I mean, you should have a Gmail ID. And how to open a Google Colab account is just follow these steps. Just go to the Google and just type Google Colab. Okay, so we'll
Sir,
get
have
the.
you explained regression?
Yeah, I will explain regression. Before that, I'm asking you to just be aware with this Google Colab, because the regression technique, the Python technique, I will be explaining in the Google Colab only. I will come back to it again. Just the
Sir,
people, someone, sorry, yeah.
sir, I thought you explained on board, whiteboard. I joined now only.
Yeah. I have not yet started completely explaining. Actually,
Okay, sir.
what I will be implementing this regression techniques in Python through Google Colab. So that's why I asked if anyone knows Google Colab. So if I mean, the people who knows Google Colab, that's okay. The people who doesn't know Google Colab, I'm telling how to open a Google Colab account. To open a Google Colab account, you should have a Gmail ID. You should be logged in with your Gmail ID, and simply you go to the Google Colab and just you type Google Colab in the Google, and you just open this first link, Google Colab. So first you just be aware of this. So you can see here there are already some notebooks are there which have done some IPython notebooks. If you observe, the notebook name will be the extension of the notebook name. You can see IPYNB, that is IPython notebook. Okay, the extension is IPython notebook. Okay, so some Google Colab notebooks I have already created. If you want, I mean, if you want to create one, you can just say from example, and you can create one Google Colab. Here, new notebook is there. You can directly create here new notebook. Okay. So when you create a new notebook, you can see a new file will be opened. It takes some seconds of time to load the file. So it is a cloud file. So if you observe the Google Colab notebook here, this is the Google Colab notebook. It consists of two things. You can see the code part and the text part. Okay. So in the code part is nothing but this cell. Okay, where you will be writing your code. Okay, and this the text part is to write some comments. I mean, whatever the text, I mean, whatever what this code is doing regarding that, you can write it. Okay, so for example, I'm just writing a printf, uh, just print, I want to say hello. Okay, so how to run this code? To run this code, you just press this play button. This button is there, right? So just click on this button. So you can see here it will be connecting to the Google Colab cloud. Okay, it will take some time to connect, just some seconds of time. Now it is initializing. So once it get connected, this cell code will be executed and you will get the result here down. See, you can see, just I printed hello. Okay, so here you can write the code, and in this cell. Okay, at the same time, if you run the code in the cell, I mean the code will be run, and you can just get the output here. Okay, so like that you can create multiple code cells like this. Multiple code cells you can create, and each code cell is independent. You can write separate code here. Okay, yeah. So I mean, you can give the name here. For example, if you are creating any file name, you can just give a name here. Just say, for example, this is demo file, so you can give demo.ipy. Okay, so when you close this file, automatically this file will be saved in your drive, Google Drive. Okay, and whatever the code you are writing will automatically saved there. So I mean, no need to save in your systems, right? So sometimes if your system fails, if you lost the data, also that kind of problem will not be there. So everything will store in your Gmail. Okay, and one more beautiful thing about the Google Colab is they provide GPUs, free GPUs. Okay, if you are doing any, I mean, big machine learning tasks which consist of big size of data, and you are running data, then you can use a GPU. So you can, if you want to use a GPU, you can see the runtime here. So just click on the runtime, and you can see the change runtime type here. You click on this change runtime type. So here there is a hardware accelerator. So which hardware accelerator you want to use? So they provide you, none means normal CPU. So GPU and TPU they will be providing. Okay, so whenever there is a need for GPU, then only you try to use the GPU. Okay, and I mean this I mean the GPUs, they won't provide you for 24/7. For the free access, they will be providing you for 12 hours. I mean, you can use this CPUs for 12 hours. If your task takes more than 12 hours and you have to save your model, and again you have to restart from the next day if you want to use freely. There is a, I mean, you can buy it also. They charge around some 1,000 rupees per month. They will provide 24 hours GPUs for you. So like that you can use. Okay. So this is how, I mean, how Google Colab works. So now let's come back to the discussion of the regression. Okay. So
So what is a TPU?
sorry,
There
sorry,
was a TPU also mentioned in the hardware accelerators. What was that?
TPU.
Yes, sir.
TPU is, I mean, it is another kind of accelerator, hardware accelerator, which, actually, I don't know what is the exact definition of it. I never used it. We use graphical processing units for larger applications. For TPU, have not used it. You can, I mean, I also don't know what actually TPU is required for. We can, I mean, you just Google it. We can look for it. Okay. Actually, I don't know what
O-
TPU is.
Okay, okay, sir.
Yeah. Next, yeah. So, okay, let's come back to our
Sir,
discussion of, yes.
sir, for what purpose are these hardware accelerators? Can you please tell?
Yeah, that's what I told you now. I mean, this, if none is selected, it is just like it's using a CPU. Okay, central processing unit. So if you are using a if you are doing any, I mean, complex machine learning task, okay. So I mean, if you have a big data sites of I mean, lakhs of images, millions of images, that time to process that information, the CPU is not enough. I mean, it will take a lot of time to process to run that machine learning algorithm. Say for example, if you are running any complex deep learning algorithms like CNNs, RNNs, in that case, and on a huge amount of data, so CPUs are not enough. So that's why we require graphical processing units, GPUs. Okay, so we use GPUs. So GPUs are faster than CPUs. Okay, so these are the, yeah, that's why we require GPUs. So normally in your system, in your normal system, what is your RAM size and what is your hard disk, and do you have a graphics card in your system which you are using?
Yes, sir. I
Ye-
have with the
Yeah.
NVIDIA GTX
NVIDIA,
1650.
yeah, yeah. I mean, better than that, Google Colab will provide you better than that GPU. I mean, it will provide P100 also. That is the best GPU which you are using. So, I mean, it will do, I mean, kind of a parallel processing it will be doing. Okay. So, it is a combination of CPUs. You can think like that. A GPU is nothing but a multiple CPUs parallelly they are running. We call it as a GPU. Okay.
High computational power, right, sir?
Yes, 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 yes. It has high computational power, and most of the people who are doing deep learning tasks, they use definitely GPU, because on simple CPU, it's very difficult for them to run. Even they run their program, also it takes some days to run the program, and moreover, we don't know when it's going to collapse. Your memory will sometimes the memory will, oh, I mean, it will be overfull or the memory will be lost. Some kind of situation always arises. Okay, so that's why normally the people use GPUs for doing high end tasks. Is that clear?
Sir, are this hardware accelerator just available in Colab, or like we can find them in other notebooks
Yeah,
also?
yeah. I mean, there are other platforms also where they can provide you. Just Kaggle also provides. Say if you see the Kaggle also will provide some online GPUs where you can run the code. Okay, Collab is
Oh,
providing like that. There are different platforms where they are providing GPUs, free GPUs. Some are providing free GPUs. I mean, free GPU means they will provide only limited time for limited time and limited normal GPU. If you, I mean, if you pay for them, if you subscribe for them, then they will provide good GPUs for longer period of time. So depending upon your task, you can check whether you can go with the normal CPU, a normal GPU, or you have to buy some subscribe GPU. Okay, so that depends upon your cost. If you can able to do it with the free version, the need not buy anything. You can do with this. Okay.
Thank you, sir.
Yeah, sure. Yeah. Now let's go into this linear regression part now. So yeah, whenever we talk about the linear regression, so here first thing first is we have to we will be talking about two variables. Okay, so here x you call it as a independent variable. Okay, and y you call it as a dependent variable. Y you call it as what? Dependent variable. Okay, so I mean that means what, the value of y is dependent on the value of x. So that's why y is called a dependent variable. And a linear regression always shows a relationship. Okay, what it will show? It show a relationship between these two variables x and y. A linear relationship between these two variables x and y. Okay, so to understand this more better, let's take an example. So I'm taking an x variable as a variable age, okay, and the y variable as speed of a car. Okay, as I told you, there are some ages. Say you are at the sub tool booth, you are collecting some cars data, and you are checking the car's age, like how new it is. So if it is just bought, say it is 1 year old, say with and it is say it is going with speed of 120 kilometers per hour, and some other age second, I mean 2 years old, it's going with say 90 kilometers per hour. Like this, you have collected some data, say 4 years and 6 years, 8 years, 10 years. I mean, it's a random data. Your wish, you have collected some data, okay, and some respective speed also you collected. Okay, so it's kind of a supervised learning. That means what? Already I know that if the car's age is 1, then I know that its speed is 120. If car age is 2, then I know that its speed is 90. If car age is 4, then its speed is something I know. Okay, so what with regression, linear regression, what can we predict is the value which I don't know. For example, I don't know if the car age is 7, what could be its respective speed. Okay, what could be its respective speed? If car age is say 15, what could be its respective speed? Okay, so these things we can able to predict. I mean, we can predict the future events with the help of a linear regression. So in order to do so, we have to build a strong, I mean, a relationship between these two variables x and y. Okay, so how means, say for example, if you draw a scatter plot between these two variables, taking x-axis, I mean x as on the x-axis, so x-axis is nothing but your age. Okay, and y-axis you take it as a your speed of the car. Okay, and you can scale for any values. Say for example, I'm scaling x-axis from 0, 1, 2, 3, like that, say up to some number 10, up to some number, or up to say some 15. Okay, similarly y-axis you say you scaling up say like 30, 60, 90, 120, like this. Okay, now if you plot this point, normally I'm randomly plotting, not exactly this. Say if the points are plotted like this, don't see this data, I'm just randomly plotting. So if I plotted the points like this, say for example, just observe the points. Don't I mean compare with this data, I'm randomly pointing these points. So some random points, some multiple points I'm pointing here. Okay, now if you see these points here, okay, if you might have observed some kind of relationship between the age and the speed, I mean x variable and the y variable. So what kind of relationship you might have observed? Can anyone tell me how the relationship is?
Positive correlation, sir.
Sorry,
Positive correlation.
positive correlation. Yeah, what is that? Positive correlation means?
That as x increases,
Hmm,
y
hmm.
increases.
Yes, correct. Yeah, whatever you said is correct. So there is a correlation here. The kind of correlation here is, see, if you see for every increase on the x value, yeah, if you see for every increase on the x value, some portions of the points on the y value are increasing. It's not linearly. Some portions are also decreasing here. You can see this point, it is decreasing. If you see this point, it is increasing. This point, it is increasing. This point, it is decreasing. This point, it is increasing. This point, it is decreasing. So like there is that means what? for every positive increase, on the x-axis, some portions of the points on the y-axis are increasing. Okay, so this correlation, as she said, rightly said, it is a positive correlation. Okay, this correlation is called as what? Positive correlation. Okay, now when the data is in the form of a positive correlation, in linear regression, what we do is we try to draw a line, okay, such that it satisfies most of these points. Okay, we try to draw a linear line. So can you, what is the equation of a line? Line is equal to mx, y is equal
Y
to mx plus,
equals
yeah,
mx
y is
plus
equal to
c.
mx plus c, right? Okay, that means what? Here y is your dependent variable, that is your speed, you want to predict speed. Okay, and x is already, this input 1 2 3, this is the age of input. If you're able to find this m value and this c value, so m is nothing but what m is called as?
Slope.
Slope, and c is called as the intercept. Okay,
Y-intercept.
yeah, y-intercept. If you're able to find out these two values, okay, then I can predict any value of x. For any value of x, I can predict y value, right? Yes or no? So if I want to predict for 12, if I want to predict, you just simply draw a perpendicular line like this, right? And you just see where this line is. Not drawing exactly. You can think of it. For example, if I want to know for this value here, say this value is 6. Okay, so just draw perpendicular on the y. Okay, so this can be possible if you can able to find out the m value and the c value. Okay, and this line which you are drawing, okay, there are multiple ways. There are multiple lines you can draw, right? Not only this straight line, you can able to draw so many straight lines here. Okay, so many straight lines, but we are looking for the best line. Okay, we are looking for the best line which satisfy most of the points, and the error should be minimum. Okay, so what is error here? So error here is, say for example, for value of 1, I have predicted, say this point, is say 35, right? Okay, this is the actual value. What is the predicted value? The predicted value is the value on the line. For 1, you can think like this. So for 1, this is the predicted value, right? The perpendicular line on the line is the predicted value, and this red here is the actual value. Similarly, for this red point is the actual value, and this is the predicted value. So this is the actual value, this is the predicted value, this is the actual value, this is the predicted value, this is the actual value, this is the predicted value, this is the actual value, this is the predicted value. Okay, so if you draw a perpendicular from the actual value to the predicted value onto the line, okay, this is gives the distance between the actual value and the predicted value, right? So if you minimize this distance should be always minimum. Okay, that is called as minimum error. Okay, so you have to look for a line in such a way that best fit the data, and the error should be minimum. We call it as standard error. The standard error should be minimum. Okay, such kind of line we are looking for. Okay, so as she rightly said, the data here is positively correlated. Okay, now for example, if my data is like this, I'm drawing like this, so points are like this, the points are like this. Now, yeah, now is there is a relationship between x and y here?
Negative correlation.
Yeah, correlation, right? So for every value of x, some portions of the points are decreasing in the y. Okay, now for this data, you tell me if the data is points are like this. The points are like this. So can you able to? There is a
Sir, no
relation.
correlation.
There is no correlation, right? You can't draw a line. Okay, so so normally we call it as correlation coefficient, CC. So correlation coefficient. So correlation coefficient for linear regression can be between -1, 0, and 1. Okay, So if it is value is -1, then it is negatively correlated. If the value is +1, then it is positively correlated, and the value is 0, then it is not properly correlated. Okay, understood the correlation? So mathematically, there is some formula. I mean, you can Google it. You can check how to find this, how to get this value. Okay. So normally you have to find the covariance, and then you have to find the standard deviation. Then you have to divide it by covariance. Which there is a formula. You can check in the Google now also, formula for correlation coefficient and how to find these values. Okay. So this is how correlation coefficient is defined. So it gives us the correlation coefficient is nothing but a statistical measure which gives a relationship between how strong, I mean, it gives how strong two variables are related. Okay. So how strong the two variables are related here. Okay. So I mean, here we will be checking the relative moments of the x variable with respect to the y variable, right? We are checking the relative moment of the x variable with respect to the y variable. Okay. So having said that, I mean, just giving a simple background regarding the linear regression. Now we'll directly jump into the code here. So I've created some code here. We directly see the code, how to, I mean, how to use these Python libraries to implement the linear regression. Okay. So yeah. Okay. Now what we have to do is, so first important library we will be importing here is matplotlib. So matplotlib.pyplot is a library available in the Python. Okay. So it is used for drawing some scatter plots, histograms. Okay. Different kinds of graphical things. If you want to draw, you can draw with the help of matplotlib. Okay. So first of all, I'm importing this matplotlib as pyplot. Plot as PLT. This PLT indicates just a aliasing name. So instead of using this total name, I can use this PLT to wrap the function. Okay. And as I said, I'm taking two variables here, x and y variable. You can see this x you can consider as the age of the uh, age of the car, and this y you can consider as speed of the car. Okay. Uh, can I annotate with this Microsoft Teams? Can I annotate it on this board? I mean, is it possible? Is there any option here? I mean, I don't know. I never used Microsoft Teams. Is it possible to annotate? Is there any option to annotate?
I don't think so, sir, but you can highlight the part of the code that you're talking about.
Okay, fine. I think I can't annotate. Okay, fine, no problem. Yeah, so this is x is the age of the car and y is the speed of the car. And you can see here, just we have drawn the scatter plot here, right? So similar way, I'm drawing the scatter plot here. So to draw a scatter plot, the code is very simple. You have to use a function called as the scatter, which is available in this matplotlib. So with the help of PLT, with a dot operator, I'm calling this function scatter. So the scatter has to between two variables x and y. So I'm passing the x variable and the y variable. Okay. When I say plot.show, it will show the scatter plot. Okay. So this is the simplest way of drawing the scatter plot. I mean, there are more complex ways also, like what is the x-axis you can do, what is the y-axis. Okay. So that thing I will be discussing in some more examples. Okay. So this is the simplest way of doing. So now you got this scatter plot, right? Okay. Now you want to draw a linear regression line. Okay. Now you want to draw a linear regression line. Okay. So draw a linear regression line. I have to use another library. Okay. That is SkyPython with scientific Python SkyPy. Okay. From this SkyPython, I will be importing a library called as stats. Okay. Statistics library stats. Okay. Along with this matplotlib. So matplotlib is required to draw the scatter plot. So I want to draw a line on this, right? A linear regression line. So in order to draw a linear regression line, that linear regression can be done available with the help of this SciPy scientific Python. From scientific Python, we are importing a library called as stats. So similarly, again, I am taking here two variables, that is x and y variables. You can see. So there is a function,
Sir,
a single line function. Hello.
sir,
Yes.
sir, we will get access to your Google Colab, or we should take screenshot of this.
No, I will provide this notebook to you after completion of this lecture. I will provide this notebook to you. I will provide this notebook to the organizers. They will share in your WhatsApp group.
Okay. And sir, SkyPy is used for importing like statistics if we have to show stats of.
Sorry, I didn't get you.
Sir, SkyPy library is used for like importing the stats, like statistics if we have to like see.
Yeah. I mean, this is a scientific Python. This SkyPy means scientific Python. You want to do statistics, NumPy, I mean, numerical things you want to do, everything can be imported from there. Okay. For linear
Okay.
regression, it is available in the stats. So that's why I'm importing only stats. Okay. I mean, you can, it's a vast thing. The libraries contain so many different functions. You can, whenever you have a time, you can just go through it. You can try. So once I provide this Google Colab notebook, you can also play with it. I mean, you can run the code here itself. You can change the values here. You see what's happening if I change values, how it's working like that. You can check, and you can run with some other functions also, which is available in the SkyPy. Okay, you can learn like that also. Okay. Yeah, fine. Now, yeah.
Sir,
Yeah,
what is the when we are using the linear regression, sir? In which situation we can use a linear regression?
in which situation means you want to predict some future events. For example, in stock market also, if there is one variable, depending upon the time, some stock is like this. So at this point of time, the stock is like this. Then you can able to predict what could be the stock price at future. So like that, if you want to predict some future events, depending upon the given single variable, you can go with the linear regression. But linear
So
regression is
basically,
a linear regression is only limited for only, if there is a proper correlation quotient also. I mean, there should be a proper coordination between the x variable and the y variable like this. I mean, if there is a positive correlation and negative correlation, then only we can able to draw this linear regression line. Okay. If the data is like this, data is distributed like this, then there is no correlation, so we can't draw a linear regression line. So this is limited to only such kind of data when there is a good correlation between the x and the y variable.
And sir, is it limited to only two variables like x and y?
Yes.
And
Yeah. As the name suggests, it's a linear thing, right? Linear means we can
yeah,
draw a, yeah. Linear means we
sir,
can draw a single. Yeah.
sir, for linear regression, like slope always has to be positive, like as you have shown.
Slope, sorry.
Slope always has to be positive only. Like it should be a straight. It should follow the straight line pattern only.
Okay, like I mean that, okay, if data is negative data here, then it can be negative also. I mean, normally data will consider numeric data like this only, not positive kind of data only. If there is a negative kind of data, then the slope will be negative always. So normally
Means
for
these
general,
two for linear regression, these two graphs are also possible, right?
which two graphs which I am showing you right now?
Yes.
Yeah, the left side graph is possible. Right side graph, there is no proper correlation between the data, so linear regression is not possible here.
Okay, sir. Thank you, sir.
Yeah.
Sir,
Yeah.
I was not added in the WhatsApp group, sir.
I mean, you can contact the organizer, then he may add you.
Yes,
You just contact the organizer, he may add you. Okay.
yes, sir.
Yeah. Fine. Yeah. Now, and one more thing is, better you can ask me questions at the end, so that there won't be a interruption in the flow. So my request to you is, if you have any questions, you just keep hold. After completion of certain topic, I will give 5 or 10 minutes of time to ask the questions. Okay, is that okay with
So,
you?
excuse me, sir. So, I want to say that if you have question right now, so please you may put up in the WhatsApp group as well. We will take up at the end after completion of such lecture. Okay.
Yeah.
Okay, sure, sir.
Yeah.
Okay, sir. Please continue, sir.
Yeah. Thank you. So yeah, now you can see here from the stats, you can see there is a method called as linear regression here. Okay, so this linear regression will take this x and y value, and it will give us this five values here. You can see it will return the slope value, it will calculate the slope value and it will return us, it will calculate the intercept value and it will return us, it will calculate the R value. R is nothing but the correlation coefficient which we are talking about, and P is the significance. I mean, this is also a statistical measure and standard error.
पूर्व डाउनलोड
Okay,
गिट
so
रिपोजिटरी दे दिया, अब डाउनलोड कर लो, अंडरस्टैंड कर लो।
can you mute?
Hi.
Please, just Karan, Prerna, please keep an eye on these things.
I mean, if you're able to mute them.
It's been done, sir. Please continue.
Yeah, thank you. Yeah, so these 5 variables values, I mean, this slope, intercept will be just we can calculate these 5 variables values with the help of single line. Okay, so linear regression, it will take the x and y value and it will calculate the linear squares of the regression, and it will just gives us this slope intercept value. Okay, now we got these values now with the help of this. So we got values for y is equal to mx plus c, we got the values of c slope value, we got the slope value, we have got the intercept value, and we found that the correlation, we can get the correlation value r. The correlation value is like this, say minus 0.65. That means what, it is near to -1, right? So it's a good correlation only. Okay, the correlation value is like 0.75 or something, so it is near to 1, so it is a good correlation only. If the correlation value is near to 0 like this, 0.01 or 0.2, so it's near to 0, right? These correlation values are near to 0, then there is no proper correlation between the x and y values. So definitely, I mean, it's a bad idea to draw a linear regression for such kind of data. Okay, so you have to, that's why these metrics are important. I mean, correlation coefficient is very much important, r is very much important. Okay, so let us see how what is the r value for our data. So yeah, now after getting all these values, now you can find the values for remaining x values. I mean, you can find the values for the remaining x value using this function. Okay, so I define a function, okay, which returns slope into x plus intercept. Okay, so it will gives us the new values. So now I this is a function defined for each x value, right? Now I have to pass each x value to this function. Okay, so in order to pass in order to pass that, and in order to build our model, I'm calling this as my model. So I'm using here a map function, which is a inbuilt library function, which is there inside the Python. Okay, so map function, what it will do is, so math function, if you observe, math function takes 2 parameters. It will take a function name, that is the function, and the x value. Okay, so x is nothing but here the iterable. Okay, x we call it as a iterable. So normally what this map function will do is, for example, x is a iterable nothing but is a list. So in Python we have list, right? So you can consider this as a list, this age is as a list. So 4, 5, 6, 7, 8, 9 values are there, for example. Okay, like this. Okay, so this map function, which is I've written here, what it will do is, so it will pass each and every value from x. So each and every value from x. So first it will take 2, okay, and it will pass it to this function. So it is pass it to the map function, my function. Okay, so what it will do, it will calculate the it will return the this total value, y value. This is nothing but the y value, right? Slope into x plus intercept is nothing but the y value. Okay, so like that, this map function will work on a given user defined function and a iterable, and for every x value we'll get the y value. Okay, so I have written in the comments also what is map function is doing, everything. Okay, next, after getting the values of y, we'll just I mean, this is the normal this y value is normal values, we are drawing the scatter plot, and this model is the values we got, predicted values, right, after drawing the linear regression, right? Okay, so when you say plot dot x comma model, then this will draw a linear regression line. Okay, when you say plot dot show, it will display the diagram. You can see the diagram here. So this is the linear regression line drawn. Okay, and these are the values which I have calculated. I mean, these are the expected values, predicted values of phi. I have printed those values here. When I say print model, it has printed the expected values. You can see these are the expected values. Okay, now if you want to predict any future value, for example, I don't know what is the speed of the car if its age is 15. Okay, so directly you can pass this 15 to the function. Okay, when you pass 15 to the function, definitely it will give what is the speed of the car. So I'm printing here the speed of the car. So the expected for 15, if the age of the car is 15, the speed I got is 76. Here you can see this is the expected speed, right? And you see the correlation coefficient also I printed here, r. So you can see the correlation is here, negative correlation. You can see the the correlation is negative correlation. Okay, and the negative correlation, how much value you got here? 0.75. So that means what? It is near to -1, right? So if it is near to -1 means what? It is good correlation only. Okay, and similarly you got the p-value, and the p-value should be very much lesser. It should be less. It shows the significance of the data. So I mean, it's you can search it. What actually p does is it again a statistical measure, and I have printed the slope value here. I have printed the intercept value, and I printed the standard error value. But you can print all this. Now, if I have a data like this, if I have a bad fit data, that means if I plot data for this graph, I mean you can see if I draw a linear regression line, so it is not fitting any of the points, right? You can see I have printed the R value, that is correlation coefficient value. So the correlation coefficient value I got it is here 0.0113, 0133. So that means what? It is very much near to 0, right? So it was near to 0 means what? It's not a good fit. Okay, it's not a proper correlation between the age and the speed variables. Okay, so similarly you can yeah you can find out for other data also. Here you can see for this data I have done this. Okay, now so this is about the linear regression. Now always data can be in the same way, right? I mean the data type we are talking about, the data which you are talking about, it cannot be in the same way. Yeah, so it can be like this also. Sometimes the data points can be distributed like this. So if I take the same example, so sometimes the data points can be distributed like this. Okay, okay, if the data points are distributed like this, drawing a linear regression line is not a good idea. Okay, so if you draw a linear regression line like this, what about the data here? So if I draw a linear regression like this, what about the data here? Okay, so in such cases we have to go with another kind of regression. We call it as a polynomial regression. Okay, that regression we call it as what? Polynomial regression. So for polynomial regression, okay, instead of fitting a line, we will try to fit a curve. Okay, instead of fitting a line, we try to fit a curve. Okay, here we take the correlation as r square. Okay, so r square means normally the correlation we talked in the linear regression is -1, 0, and +1. So when I say r square, the value will be 1, right? Because this square, it can be 1 or 0. Okay, so that means what? If the correlation coefficient in polynomial regression is near to 1, okay, near to 1, that means what? That is a good correlation. If it is near to 0, that means it is a bad correlation. Okay, now let us take some data here and we'll try to plot the polynomial regression line also here. Okay, so for example, yeah, I am taking this data. You can see this data here. So here I am taking x value and the y value. So x value you can consider as the hours, okay, hours of the day. So you are at some tool booth, you are collecting at each and every hour, you are collecting some speed of the car. Some cars are coming there, you are collecting the speed of the car. So at the first hour, a car came whose speed is 100 kilometers. Like that at second hour, these are relative speed, I mean relative hours and relative speeds. You can consider it the third hour at 80 kilometers car came. At 22nd hour, say some car with 100 speed has come. Okay. Now, if you want to find a missing data, for example, you don't know what is the speed of the car if it has come at the 17th hour. Okay, that thing we can able to find it, right? Now, if you draw a scatter plot, so already we know that we have to import this matplotlib library. Again, you are taking the x values and the y values here. Okay, and you are just scatter plot. You are drawing a scatter plot here, x and y, and you are showing the scatter plot. So you can see that scatter plot when you draw, it's not applicable for linear regression line, right? So the data is not applicable for linear regression line. Here you have to go with a polynomial regression. Okay, when I say polynomial regression, so here the concept of line will not be there, right? The concept of curve will come here, right? So this will not suffice. Okay, so what is the normally we have to go with some degree polynomial, right? For example, if I go with a 2-degree polynomial, the equation of the 2-degree polynomial will be like this, right? So if it is a t-degree polynomial, it will be like this, right? X cube plus vx square plus cx plus d. Okay, so you can fit any degree polynomial, that is your wish. We have to just with the help of using this Python libraries, we have to check which degree polynomial can best suit for our data. That is trial and error only, and that can be done. You can just changing the degree of the polynomial, and above that you have to find these quotients also, right? In order to predict a new value, you have to find the quotient of this x square term, you have to find the quotient of this x term, and you have to find this c term also, right? If it's a 3-degree polynomial, a, b, c, d, these 4 terms you have to calculate. All these values will be calculated automatically with the help of this library here. So here, what we'll be doing here is, check here how we are trying to fit a polynomial regression curve here. So I'm saying that I'm using a my model here. Okay, so it is available in the NumPy for writing this polynomial regression thing. It is available in the NumPy numerical Python library. Okay, so I'm using NumPy. So I'm using here poly1d. Inside that, again I'm using numpy.polyfit. Okay, so just see here, there are two functions I'm using here. Okay, with the NumPy, you can come from this side. This is polyfit. So polyfit function, what it will do is it try to find a polynomial degree curve which can best fit this data. Okay, so for example, here I have given xy is nothing but these values, and the 3 indicates the degree of the polynomial. Okay, what does 3 indicates here? 3 indicates the degree of the polynomial. Okay, I tried with different degrees of the polynomial. I got at 3, I got the best curve like this. So I fixed with 3. So polyfit, what it will give? So polyfit takes our data, x and the y value, and by looking at this data, I try to fit a best line, best curve, not line, sorry, best curve. If you change this degree, the curve will also change. Okay, so if the degree is 1 here, then it will automatically become a line, right? A polynomial degree 1 is nothing but a line. Okay, so for 3 degree, I got this curve. Okay, and this poly1d function here. Okay, this poly1d function helps us to get a good polynomial like this. Okay, it helps us to get a good polynomial model. What is the x value, what is the y value, for x and y value, how we got the polynomial, this will do. So that's why we are using this poly1d function. Along with that, we are using polyfit function. Okay, now this myline function, it specify how the curve should display. What is the starting location of the curve and what is the ending location of the curve. Okay, so this numpy.line space, it will be decided by that. For example, if I want to start the curve at the first location, you can see 1 to 22 means what? 1 is the starting location. You can see here. You can see in the curve here, graph. So at 1 I am starting. You can see carefully. At 1 I am starting, and where I am ending? I am ending at 22. Okay, so this is starting location. This is 22, and this 100 specify the points. How many points you want to divide this total curve into. So it's nothing but the combination of 100 points. This curve is nothing but the combination of 100 points. Okay, so so first parameter indicates the start, that the start of the curve. Second parameter indicates the end of the curve, and this 100 indicates the number of samples to generate. Okay, so when you say plot.scatter, first the normal scatter plot will be drawn, and when you say plot this plot my line with model my line, then it will draw the curve, polynomial regression curve upon the scatter plot. Okay, when you say show, it will show on the screen. Okay, and you can print the values of the my line, and you can print the values of the my model. So these are the 100 samples we told you, right? So all the values we have printed here. Okay, now you can see, you might be getting doubts, sir, why 3 only? If you want, you can check with 2. For example, if I'm checking with 2, if I run this code, you can see I'm running the code. It is initializing. It is connected. Now see the change in the curve. So is the best curve? Yeah, it's not the best curve, right? Okay, so you change the value to 3 and check it now. So it's a trial and error only. So it is the best curve now. Okay, so if you make it as 1, it will become a line. It is a line. Okay, so similarly for you look for the what we call linear bound, best linear bound, lowest linear bound. For 4 also you're getting best curve, but I'm getting it best for 3, right? Why we require to go for 4? Because if I go for 4, again a lot of computation has to be done, right? I need to find out the different quotient values. So for 3 I'm getting the result, so I stop at 3 and I'll see the curve. Okay, now you can see the polynomial regression equation also here. So the quotient of x cube is, this is, I said that the curve is of degree 3. So this where this model is, it is placed inside this model, right? When I print my model, so you got the polynomial equation. So x cube minus this is the x cube quotient, this is x square quotient, this is x quotient, and this is d value, right? You got these values also. Okay, now as I told you, we use r square here to find out the correlation between the x and y. Okay, and to find the this r square, again it is available in the scikit-learn matrix, scikit-learn sklearn matrix. Okay, so from this scikit-learn matrix module, we'll import this r square score. Okay, so what it will do is it just gives the r square score. So for example, we are taking the same data here what we have taken. For this data, I want to know what is the r square value, right? Because this curve is fitting here best means what? There is good r square score, right? So what is that r square score? Let us find out. So you just take x and y values, and with the model, you are fitting the model. After fitting the model, you just say print r square, okay, y comma model of x. You pass these values. So you can see the r square value I got is 0.943. That means what? It is very much near to 1, right? This value is very much near to 1. So that indicates what? That indicates our there is a good correlation between the x and the y variables. Okay, yeah, any questions here up to now?
Sir, I have a question.
Yeah, please.
Sir, after we make the graph, like after plotting the graph, we then check the R square value that it is fitting properly with the correlation to x and y.
What? Yeah. After drawing the graph, you are checking the correlation value x and y. Yeah, I mean, yes, yeah, we are doing that thing only here. According to this code, what we are doing, after drawing the graph only, we are checking here what is the correlation value. Why? Because see, I mean, normally for I mean, in linear data, the data we can assume like if it is like this, the points are distributed like this. Here also we'll see that the correlation value after drawing this only. I mean, how much this how the data is correlated. For this also, you can see for when the data is like this, definitely by intuitively you can get an idea like, so the curve should be like this only, right? Okay, so this curve only deciding how correlated the data is. Okay, so that's why after drawing the curve only, you can see we are finding the r square value here. Okay,
Sir, if R square value comes close to 1, then it means that it is going to be a good correlation, right?
yes, correct.
Okay, sir.
Yes, so r square value is near to 1, then it is a good correlation. If r square value is near to 0, then it is not a good correlation. That thing also I will show you now. For example, you take this data now. Okay, say this data, and I am fitting a model here. Okay, hello, yeah. For example, no, I think this is the same data which I have taken. Now I'm predicting a future value. For example, for at fifth hour, what is the speed of the car I want to predict? So I can predict it directly by passing the value 5 to the model. Okay. Now in this example, you can see I'm taking another example here where the data is like this, and you can see the data is like this. So you can't able to fit a line, I mean fit a curve here. Okay, if the data is like this, you can't able to, this is a bad, we call it as a bad fit. And for this I have calculated the I mean we are calculating the r score here. See, I'm calculating the r score after fitting the model. You can see the r square value is very much near to 0. It is 0.0099. So it is very much near to 0, right? It is, so it is a bad fit. Okay, we can say that is a very bad relationship exists between this data, so it is not suitable for polynomial regression. Okay, this data is not suitable for polynomial regression. Okay, so this is about this linear regression and polynomial regression. Okay, now till now, see, we have been working on data types, data sets, which are very, which consist of only two features, right? Yes or no? We can consider as x is one feature, y as another feature, or you can consider as x as an independent variable, y as dependent variable, or you can consider y as a class label and x as a observation. Okay, so there are different names can be given to these variables. Okay, so till now we were talking about only two variables, right? Okay, so what if for example, if I have three variables like this, x, y, z, okay, and say the decision of the y variable, say this x and y are these are dependent variables, okay, and y is independent variable. Sorry, this is independent. X and y are independent variables, and y is the dependent variable. Okay, and I can predict. In order to predict the value of z, I need to consider both x and y values. Are you getting the point? Till now, here y is dependent on the single variable. Here, the y is dependent on the more than one variable. Yes or no? Okay. So if such kind of data is there, then normal simple linear regression or polynomial regression will not work, because the dependent variable is dependent upon more than one independent variable. In such cases, the linear regression and polynomial regression will not work. Okay, for that kind of situation, we have to go for another kind of regression technique. Okay, such regression technique we call it as MLR, multiple linear regression. Okay, so what is one MLR? We just take an idea. So for example, the data set I will be using here for MLR, consider like this. For example, I have uh, uh, 3 points, like I have point, say I'm considering a points on data, say for car data only, have it car data only. Okay, say for example, I am considering, right, there is a weight of the car is one variable. Weight of the car is given. I'm talking about some car data. Okay, and these are the data is available with me. Say weight of the car is available with me, and the volume of its engine is available with me. Weight of the car is available, volume of that engine, the car's engine volume is available with me, and also available this carbon dioxide emission, how much carbon dioxide emission the car is emitting, how much of pollution it is emitting. Okay, so for example, if the weight of the car is say 1100 kilograms, okay, and say volume is say some 100, like this, some metric is there, cm cube. Okay, and carbon dioxide it is releasing is 50 grams of carbon dioxide it is releasing. Okay, so like that I have some data like this, I have some data. Okay, now I want to predict what is the carbon dioxide emission of a car, any car, given its weight and volume, and new values of weight and new values of volume if I give, okay, which is not there inside this data. If I give you a new volume weight of a car, and if I give you a new volume of the engine of the car, then I need to predict how much of pollution it is released. Okay, that means what, here this variable, carbon dioxide variable, is dependent on the volume of the car, as well as it is dependent on the weight of the car also, right? So this kind of problem we call it as multiple linear regression. Okay, so that means if I write it in mathematical terms, this same thing, if I write it in mathematical terms, I can write like this, right? So if I want to find out the carbon dioxide emission, okay, so I need to find out what I need, it should be dependent on weight, and it is dependent on volume. Okay, for this some quotients will also be associated, right, like beta 1, beta 2. So these are the quotients associated with weight and the volume. Okay, just like we are trying to create a three-dimensional space, okay, where the points are like this, and we are trying to draw a perfect hyperplane. Instead of drawing a linear line here, we are trying to draw a hyperplane which satisfy these 2 points and can predict this. Okay, visualizing this is something difficult. Anyhow, in the next session of my lecture, I will be showing you how to visualize these 3D plots, because till now we were visualizing only scatter plots, right? Because I have x value and y value. Okay, here I have x, y, z values, right? That means what is a three-dimensional visualization. We have to visualize three dimension. When I talk in linear terms, it is a we're talking about line. When you are talking in three dimension, we talk about a plane. Okay, so the point to be told here is what? So this the carbon dioxide variable is not only is dependent on the weight factor, and also it is dependent on the volume factor. Okay, and this beta 1, beta 2 here indicates what? Beta 1, beta 2 indicates the quotient of the variable weight. Beta 1 is the quotient of the weight, and the beta 2 is the quotient of the value. Okay, are you getting the point? Okay, and there will be an extra term here, beta naught, which is an intercept. Okay, that we talk, we will not talk much about it. Okay, so before going to the code, first of all, I will show you the data set here. Okay, you can see the data set here. So I have written some notes here you can take. So what is the objective here? I want to predict the carbon dioxide emission of a car. Okay, given the size of the engine, that is volume of the engine, and what weight of the car. Weight of the car is given and the volume of the car is given. So that means what? We have to throw more than one variable, right? Okay, to make a prediction more accurate. Okay, so you can see this is the data set. You can ignore these first two columns, because they are not providing much data. I mean, not important data. Just they are giving the car name and model. That is not much useful here to predict. Only thing we will considering is we will considering on these three variables. These three. Okay, volume, weight, and carbon dioxide. You can see this is a total data. Okay, so it contains some number of rows. Okay, so now this data is in the form of a table. In Python, we have something called as already you were discussed about list, right? You know what is a list is, right? You know what is a tuple is. Okay, in yesterday's and previous classes, I think these two have been discussed about list and tuple. Okay, so there is another thing called as data frame in Python. Okay, df. So what data frame will do is it will store multiple lists like in a form of a table, like this. Say this is list 1, list 2, list 3. So it will store in a form of a table. Data will be stored in a form of a table with the help of these data frames. Okay, so these data frames are available in a pandas library. We will talking about it. It is available in the pandas library. We have to import this pandas library in order to access these data frames. And the data set of cars which I have, this cars data set I have in a form of a CSV file. I have stored that data set in a form of a CSV file. So can anyone tell me what CSV file is?
Sir, it's an Excel file. Yeah.
Yeah, Excel file. We call it as a comma separated file. Comma separated values. Okay, comma separated values. Okay, so the file of the car data set is stored in a form of CSV file with me. Okay, I need to load this data, right, in order to perform this multiple linear regression. First I need to load this file into my system, Python system. Okay, so I have to load this in a form of a table. Okay, so this CSV file will be loaded in a form of a table with the help of data frames. Okay, so these data frames can be accessed using pandas library. Okay, so when you see the code, it will be much clear for you. So normally how this cars.csv file will be is, so it will be like this. So weight, comma, volume, comma, carbon dioxide emission, comma. Okay, this is n. Then say weight is 1000, comma, volume is say 100, comma, carbon dioxide is 20. So all values are separated with comma. So all rows are stored like this. This is first row, that is the label. Second row is the value, third row value, fourth row, like that. Any number of values, they are all separated with comma. Okay, I will show you the file. One second. One second, I will just the file is with me. I will show you. Where it is. Give me a second. I'm searching for Mm. Oh, 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 oh. I have kept it here only where it has gone. FTP. Oh, without that file also I can't run this code now. Cards.csv. Just give me 1 minute. I will just search it. Again, I will share the screen with you. Mm, where I kept it. Let me check it is available in my mail. Yeah. Yeah, I got the file. Is my screen visible? Am I sharing my screen?
No, sir.
No, no.
No, sir. No,
Yeah,
sir.
one second.
Shared, sir.
Shared, right? Yeah, just downloaded the file. Sorry for the interruption. I'm showing the file. This is the cards.csv file. I'm opening it with the edit plus plus notebook. So you can see the data like this. It's opening. Just give me a second. Yeah, see, can you see this? So all fields are comma separated, right? Car, comma, model, comma, volume, comma, weight, comma, carbon dioxide, Toyota Argo 1790. So like this, we have 37 fields, right? 37 rows we have. First row you can ignore it. From second, that means 36 rows are there, which contains data. Can you see the file, everyone? CSV file, cards.csv
Yes,
file,
sir.
Yes.
and comma separated file. Okay, now let's go to the code now. Okay, as I said, we have so the file is in the form of a CSV file. So in order to read a CSV file, we require a pandas library. Okay, and one more thing is to implement this multiple linear regression model, we have to import a linear model which is available in the scikit-learn. Okay, we have to import this linear model which is available in the scikit-learn. Okay, so first of all, what we have to do, we have to read the file. Okay, so what is the procedure for reading the file? So just create a data frame. As I told you, data frame is nothing but which stores the information of the file in the form of a table. So you use this pandas library. So pandas dot, the function is read CSV, read underscore CSV, and you have to give the path where the cards dot CSV is present. Okay, see, right now I'm running my program in Google Colab, right? So when you run the program in the Google Colab, you have to import that file to your Colab environment. Okay, so without importing that file to the Colab environment, if you run this code, you will get an error showing that the file does not exist. So I'm running this code. For example, if I run this code now, you'll get an error saying that the file is not found because I have not uploaded the cards folder, cards file here, right? So how to upload that file in the Google Colab environment? You can see when I click on this file box. Okay, so you can see a upward arrow here, right? So from here you can upload the file. So just click on the upload. So you just go to the downloads. I have downloaded just now. I downloaded in the download. So from there I have just uploading the cars file. Okay, while uploading, it will give some kind of warning message saying that so these uploaded files will be get deleted when this runtime is recycled. That means what? When you close this Google Colab notebook, okay, automatically this file will be deleted. That is the meaning of that. Okay, again, if you want to run this code, again you have to import this cards.csv file. Okay, now if you want to know what is the path of this, you just right click on this and you just copy the path. Okay, and you just place that path here. So I'm placing the path here. So this is the path, only same path, so it will be pasted here. Extra slash has come. Okay, so this code, you can see I'm just reading the file. I'm storing it in the data frame. Okay, now the beauty of the data frame is you can individually, it's very flexible. You can individually retrieve the columns. For example, what is the x variable here in this case? When I talked about this uh, I'm talking volume, weight, volume, and carbon dioxide relation, right? So you can consider these two as x variables, right? W comma v as x variable, and y variable you can consider as carbon dioxide. Okay, so if you want to find only what table consisting of only weight and volume, you can directly retrieve using this Python notebook. That is x. So x is also a data frame. So this data frame consists of only, say I'm calling only weight and volume. Okay, so this will make a list of independent variables, and this is a list of dependent variables. So two lists I want, right? One is independent variables. So weight and volume are the independent variables, and this is the dependent variable. Carbon dioxide is the dependent variable. Okay, so if you print the data frame, this data frame, you will get the total table. If you print only x, you will get only weight and the volume. Okay, so just I will run it. Later further the code I will explain. You can see. So you can see. So this I'm printing the data frame. When I print the data frame, total data frame, it's printed in a form of a table. Okay, and I printed the x means what? Weight and volume. So only x column, weight column, and volume column is printed. This left hand side, this is the indices, just the indices. So it gives the index of the row. Okay, so now come to the code. Now I want to put a multiple linear regression model, right? So the code is very simple, straightforward. So from I told you that for fitting the multiple linear regression model, you have to import this linear model. Okay, so I imported the linear model from the scikit-learn. So here you just say linear model dot linear regression. Okay, so what happens is when you call this, when you put this linear regression method, what it will do is it will create a linear regression object. Okay, and when I say regression dot fit regr, this is the variable I have taken. When you say fit x comma y, so x is nothing but your independent variables, y is your dependent variable. Okay, so when this fit object is called, this fit object takes this independent variable, that is weight and volume, and the dependent variable carbon dioxide, and it will fit a regression, actually hyperplane, and which hyperplane will be fitted. I mean, a multiple linear regression model will be fitted by using these 2 lines of code. Okay. Now, for example, you can predict the carbon dioxide for a given weight and volume. Say I have given here volume as weight as 2300 kgs, which is not there in the data, and I have given volume as 1300 cm cube, okay, centimeter cube, which is not available in the data. Then I can predict using this regression dot predict. Just give this, pass this value, and you can print the predicted carbon dioxide. Okay, so the carbon dioxide which I have predicted for this is, you can see I have predicted here. So I got here how much? 107 grams of carbon dioxide it is releasing. Okay, so this is the simple code for multiple linear regression. This is a simple code for the multiple linear regression. Okay, now see the importance of the quotients here. So if you take this quotient, if I want to specify the importance of this quotient, so here what we got, the quotients of what? Weight and volume, right? I got the quotients of the weight and volume. Okay, so here x is the weight and volume and y is the carbon dioxide. I'm fitting the model. And if you want to know what are the quotients of the weight and volume, you just say regression dot quotient. Okay, you have to just implement the model and just print regression dot coef underscore. So this gives the quotients of the weight and this gives the quotient of the volume. So these are the quotients of the weight and volume. Okay, so what is the importance of quotients here? So that means what? For every 1 kg increase of weight, this much carbon dioxide gas will be increases, right? Because it is a quotient. Similarly, for every 1 cubic meter cubic volume increases of the engine, this much carbon dioxide gas will be released. That is the, I mean, that is how the quotients are there, right? Okay, so that is what I discuss here. So if you want to cross check, you can cross check here. So earlier we found out for 2300 kgs and 1300 volume, right? Okay, now I want to find for 1300 kgs, 3300 kgs. The value we are getting here was the 114. Okay, the same thing we can do with the help of quotients also like this, because for 2300 kgs already we know that the value of carbon dioxide released is this much. Okay, now this weight is increased by 1000 kgs, right? So if you just increase the quotient with 1000 times, so quotient of this weight is already we predicted, right? The quotient of weight is this much. So if you multiply the quotient with 1000, okay, and if you add it with the previous thing, you will get the current value as 140. Okay, so I mean, this is I'm showing the importance of the quotients to cross check your values. Okay, so this is about the multiple linear regression. Yeah, if you have any questions, I'll take the question before producing to the next session.
Yes, sir, I have a question.
Yeah, please.
Sir, we should check for the model assumption side if there are any autocorrelation, multicollinearity, homoscedasticity. We are not talking about that.
Sorry. Hello,
Like,
please.
sir, there are
Can you repeat?
hello.
Can you repeat your
Yes, sir.
question?
Yes, sir. There are certain assumptions for the multiple linear regression model. Like is there any autocorrelation, multicollinearity, homoscedasticity of the observation?
Yeah. I mean, the main aim of my today's session is I will be discussing more about the code, and mathematically I will be discussing this. So that's why my aim is to show how these models can be done with the help of Python programming. So that's why I introduced different libraries. So my scope is restricted to discuss only the coding part. The mathematical part, I mean, there are so many things. If you go into mathematically, it is so many things are associated with it. Okay, so that's thing I'm not discussing here. I was only concerned more about the coding part.
Yes, sir. But
Hello,
if
sir.
we don't check for like multicollinearity, then we can even the coefficient will be in opposite sign as well, and our model will predict in the wrong way.
Sorry, multiple dimension. What you are saying?
So multicollinearity, like if two independent variables are also dependent on each other, we may find correlation between the. Then the coefficient will be like in opposite signs as well, and the model will predict.
Yeah. There is a possibility. Yes. Whatever you are saying is correct. Yeah. Yeah, for such cases, I mean, if the data is such case, yeah, I will discuss in the second session where what we have to do for such kind of things. I mean, in exploratory data analysis, we try to visualize data in much more different terms and see how this multidimensional data can be classified. Okay, that part I will discuss in the second session. Yeah. Any other questions?
Sir, from sklearn import linear model. What was linear model, sir?
So linear model is nothing but a package which is available in the scikit-learn. Okay, so this linear model package only contains the multiple linear regression model. Only this, with the help of this model only, we can construct the linear regression model, multiple linear regression model. It is available there in the scikit-learn.
Okay, and sir, sklearn is for like what purpose?
Yeah, it is also one a machine learning Python library which contains machine learning algorithms. So in scikit-learn, you have different algorithms like support vector machines, random forest, deep CNN architectures you can build, RNN architectures you can build. So a lot of machine learning algorithms are available in the scikit-learn library, this module.
Sir, random forest we will do in this course.
Random forest we might not be doing. I mean, we restricted for this only regression and classification techniques, which I am going to discuss it next topic.
Oh,
Random
okay,
forest,
sir.
yeah. I mean, there are lot of things actually to be discussed, but that the time is very much limited, right? So it is a big
Sir,
course. I mean, it contains a lot of things to be discussed. So
sir, you
whatever the
can take
time
one extra class.
I mean, yeah, definitely. I'll try to. If organizers allot me to take a extra class, definitely I'll take a class and I'll explain you about the random forest. That is very interesting topic. I want
Yes.
to. Yeah.
Sir, good evening, sir. I have one question, sir.
Yes, sir. Please,
Sir,
sir.
we have seen polynomial regression, multiple regression, and linear regression. I
Okay.
have a confusion where we can use the polynomial, multiple, linear regression.
Sir, only thing is that's what we are talking about, right? I mean, depends upon the type of the data which we are using. So better
Okay.
is you first visualize the data. Okay, you try
Okay.
to put the data in some scatter plot or some pie plot or some histogram.
Yes.
Then you, if you visualize the data, I mean, before doing any machine learning analysis, first we have to do exploratory data analysis. If you
Okay.
visualize the data properly, then we can decide which kind of algorithms we can use. Okay, so for all
Okay.
kinds of data, this kind of techniques are not suitable.
Okay.
Only for some kind of data, only this kind of, I mean, whenever there is proper correlation between the variables, such kind of data is, I mean, this kind of techniques will be useful.
So how we classify independent variable, dependent variable? I have some.
Yeah. I mean, see, for example, I mean, that I mean that according to data only. For example, if the age of the car is given, you are predicting something.
Okay, sir.
Okay. The depend. Hello. Yeah. The if something is given, I mean, if a label is given, that is the predicted variable. That is called as the dependent variable. I mean, by looking at the data only, you can think. Okay. This identification of labels also, I mean, for example, you have a some disease data set, right? Okay, in disease data set, you have to identify whether the person has a cancer or not. So depending upon some parameters, you will say that this person has cancer. So all these parameters will become the independent variable, and the variable at the last, the cancer, if this parameter is satisfied, if it has a cancer, that becomes the dependent variables, because if all these parameters are there, then only he has cancer. So like that, by looking at the data only, you can identify the dependent variables and independent variables. Yeah, any other questions?
Sir, how do we decide how efficient the model is, like how accurate the answer is?
For that purpose, see, till now, what we are doing is in the regression, for accuracy, you can think in terms of error. I mean, the predicted value and the expected given value. The error is minimum, then you can say that that much that your model is accurate for regression problems. For machine learning and different algorithms, like we talk about support vector machines or some decision based algorithms, there we have to find out accuracy. Accuracy is also the same thing, like first we'll train the model with training data, and we test with the test data, and with the test data we try to validate how much with what accuracy the model is trying to predict. Okay, and there we built a confusion matrix, like if it is true, the model has predicted true or false. So like that will compute for how much cases it has predicted correct, how much cases it has predicted wrong, and finally will predict the accuracy.
Sir, in Pandas library, there is method called read_CSV. So suppose I have some PDF file or text file. In that scenario, what?
Yeah, for different files, there will be different methods. For CSV, read_CSV. For JSON, I think read_JSON, like that. For different files,
But
the different methods will be there.
this file we read and we'll get some that what is it, that DF data factor, no? We
Data
are getting
frame.
it as a data frame we are getting. But in
Yeah.
data frame, suppose if I for one row I have some different like name and roll number. In the second row I have something like name and address. So how we can means handle this scenario?
No, data frames are only for storing. Okay, for storing whatever the CSV file is there, however the data is there, in the same way it will be stored in the data frame. Okay, we are not going to manipulate the data, any kind of operation, but we can do some kind of numerical operations on the data. We can't, I mean, if you want, you can manipulate also using NumPy libraries. Data frames are only to store the data, and you can perform some numerical operations.
Okay, so whatever the data which is available in that CSV file, Excel file, the data is nothing but
Yes,
just a copy paste in the data frame.
Yes, correct,
And
100%. Yeah.
Okay, so based on the
Sir,
requirement, we will go for the
excuse me, sir.
process.
Yeah. Yes, madam.
Sir, do the neural networks work using linear regression or polynomial or ye multilinear?
Madam, neural networks are, I mean, these regression techniques are completely, again, you can call neural networks again. I mean, it's not like that. Only thing is, how can I tell you? So neural networks are used for classification. Okay. So the neural networks are used for classification. They will also classify. I will give a good example, like for example, say simply I will take a simple example of, say, for example, say OR gate. If I want to get a OR gate, if I want to realize a OR gate, so in the OR gate I know that if do values are 0, then it is 0. For any other value is 1, it is 1, right? Yes or no?
Yes. Okay, sir.
Yes, sir.
Yeah. So for this, say this is 0.0, x value is 0, y value is 0. Okay. So this is 0, 1. This is 1, 0. And this is 1, 1, right? Now, what neural network will do is, if you train a neural network, simple neural network like this, which takes this x value and the y value, okay, and it will give some output. So this output again depends on this output is nothing but the summation output, along with it will be passed to a term transfer function or activation function. Okay. So normally what this neural network trying to do is, it trying to look for a line, okay, which can separate, because see, this is class 0, right? This is only class 0. Remaining things are class 1. This is class 1, this is class 1, this is class 1. Yes or no?
Yes, sir.
So neural network is trying to classify these 2 points. I mean, if any points coming in this direction, I say it belongs to class 0. Any point coming in this direction, I say it belongs to class 1. So neural network is trying to draw a line. I mean, just a kind of a linear line only. Okay. So it's trying to classify like this. I've given simple example of OR gate. Like this, the data type the data can be any type. Okay. So linear, if you take any machine learning algorithm, mathematically, what it will try to do is it try to draw a linear line. So and it say that whatever the data coming in this direction, it is a negative data, and whatever the coming in this direction is a positive data. So mathematically, all models are doing the same thing. This thing only. Okay. So here regression means what? Regression, I'm not, I'm drawing a line, but I'm trying to draw a line to fit a data. I want to predict the future values. Okay. Here it is doing classification. Here it is doing what? Classification. Classification between the negative points and the positive points. Okay.
Okay.
Yeah.
Okay,
I mean,
sir.
if you can learn more about the ANNs, then you can appreciate the importance what how they're working. Yeah. Shall we go for a break for 5 or 10 minutes now? And next session I will start with exploratory data analysis. That is also very interesting session.
Sure, sir.
Yeah, thank you. So I will be taking a break for 5 minutes. So it is 8:47, right? I will come back at 55. Okay. So 8 minutes break. I'll come back at 55. We'll start the session at 55. Okay. 55 or 7 o'clock. Okay.
Okay, sir.
Okay, sir.
Anyone knows what is polynomial regression?
Hello. Is my voice audible?
Yes, sir.
Yeah, thank you. Shall we start?
Yes, sir.
Yeah, thank you. So, okay. So in the next part of my session, this session, I will be, let me share my screen. Please let me know whether my screen is visible or not.
Yeah, visible.
Yeah, thank you. So yeah, here we will be doing a topic called exploratory data analysis. Okay, EDA. Okay, so I mean before the main important step before we are going to apply any machine learning algorithm to any data, so we have to visualize the data. Okay, so normally this exploratory data analysis is refers to a process. I mean it is a process of uh, prior investigation of data. We call it as a prior investigation of data. Okay, so why we have to do this prior investigation is to discover any some kind of patterns. Okay, to discover patterns. With the help of these patterns, we can able to find if there is any kind of anomalies are there in the data, or if able to find any kind of assumptions we can make from the data, or we can also able to design some models, some basic models by just visualizing the data. Okay, so in the exploratory data analysis, mainly we will be drawing, we will be looking the data graphically. Okay, so we will be looking the data graphically in graphical terms. Okay, so mostly we'll try to plot some graphs, like already we plotted scatter plots, right? So we try to plot some scatter plots. Okay, we try to plot some histograms, and we'll do some PDFs, probability density functions. We look at some cumulative density functions, and we'll do some univariate and multivariate analysis. Univariate and multivariate analysis. Multivariate means multivariables analysis. Okay, so till now we have seen three-dimensional data, right? 3D data. Okay, so what if we have data with more than more than 3 dimensions? I mean 4D dimensions data. Okay, so here for doing this EDA, I will be taking one toy data set. Normally, this data set name I call it as a iris flower data set. Iris flower data set. I will be using this data set. I will show you the data set first. Okay, and I'll talk about this data set. Okay, so this iris flower data set, it consists of four features. So it consists of sepal length, sepal width, petal length, and petal width. Okay, and last column is the what kind of flower it is. Okay, this sepal length, sepal width, petal width, these are the values. Given these four values, I can say this is iris flower. Okay, again this iris flower has three species like iris setosa, iris versicolor, iris virginica. Like that, there are three species are there. Okay, first I will show you the data set and we'll try to do exploratory data analysis on that data set. Okay, so plotting exploratory data analysis. So this is another new Google Colab file which I opened already. I have done the code here. So I opened this. So before going into that, we just look at into some basic terminology. So as I told you, why we require what is EDA is. EDA is exploratory data analysis. It is a process of performing some kind of operations, that is initial investigations on the data in order to discover some patterns. Okay, so you know what is a data point and observation, right? I mean, if I take mm, this thing, for example, if I have a data set like this, which contains some rows and columns. So this is feature 1, say this is feature 2, say this is feature 3, like that feature 4, and finally say I have a class label L. Some rows and some columns are there like this. Okay, now each row is called as a observation. So what is the meaning of this data point or observation is each this value is called as a observation. Okay, now what is data set? Data set means this total complete data observations, collection of this data observation, we call it as a data set. Okay, and what is feature, variable, input variable, independent variable? So these are our features. These are also called as input variables. They're also called as independent variables. and this final column we call it as a class label or dependent variable. Okay, if you take any data set, this will be the terminology. Okay, so the flower, can you please mute yourself? Yeah, so the flower data set which I am consider here is iris flower data set. So you can go to this Wikipedia page of this iris. I have provided a Wikipedia link here. When you click on it, you can open, you can see it is opening a page, a Wikipedia page here. Oh. Hello, is my voice audible? Hello.
Yes, sir.
Yes, sir.
Yes, sir, it is audible.
Okay, I mean when this internet is not, yeah. So as I told you, I'm showing you the iris flower data set. You can see. So you can see the flowers here, right? There are three types of flowers. Okay. So the main objective, I will tell you what is the objective, what we have to do. So you can first you look at you observe the flowers here. So this flower we call it as the iris setosa, this flower, and this flower we call it as the iris versicolor, and this flower we call it as the iris virginica. Okay, for all these flowers, a scientist by name Ronald Fitch, what he did is he has collected some data set, okay, based upon these values. Okay, so what values he corrected is he had taken the values of sepal length, sepal width, petal length, and petal width. Okay, so the sepals and petals are related to the flower. Okay, what are sepals and petal? I will tell you what is sepal length and petal length. Okay, so he has collected some 150 observations. You can see this is a somewhat big data set which consists of 150 observation, and you can see for every 50 observations he has divided these three flowers. These three flowers are there, right? So for iris setosa he had made some 50 observations. You can see, so first 50 observations, it tells that these values of sepal length, sepal width, sepal petal length, and petal width, given these four values, is classifying that flower as iris setosa. Okay, I mean given these four values, he is classifying the flower as iris setosa. Okay, similarly from 51 to 100 values, given these four values, he is classifying this flower as versicolor. Okay, similarly from 101 to 150 values, given these four values, he is classifying this flower as virginica. Okay, like that 150 observations he has made. Okay, so now these observations are made by Ronald Fisher. He is a botanist, he is a scientist. Okay, so in 1936 he has made this. Okay, now the objective of this topic is to classify a new flower as belonging to any one of the three classes given the four features. That means what? If I give a new feature, okay, for example, if I give new sepal length, if I give new sepal width, if I give new petal length, and if I give new petal width, which is not there inside this data set, which I have shown you, which is not there inside this data set. If I give new four values, you have to tell me, if given these four values, you have to classify the flower as either iris setosa or iris versicolor or iris virginica. So this is the objective. The objective is clear. Yes, the objective is what? Given these four values, I had to classify the flower to any one of this classification. I mean, any one of this class. Okay, that is the objective. Okay. Now, yeah, here I need to talk about the importance of domain knowledge, because before applying any machine learning algorithm, the data which you are collecting, that is of utmost important. Okay, because without proper domain knowledge, if you collected any random data, if you run a machine learning algorithm on it, it will just becomes a number crunching game. Okay, you won't get proper result, you won't get proper outcome about it. Okay, so that's why before applying any machine learning algorithm on the data, it is better, it should be important that your data should be uh, collected from a good domain expert, or if you don't have a domain knowledge, you have to consult a domain expert. You have to collect the data from there, because for example, if you want to predict whether a person is having some kind of disease or not, okay, what you will do, you have to collect the data set, right? Where you will, who will you will consult? You'll go to some hospital, some institute, Ontology Institute, you will go there and you will collect, you will consult the doctors, and they will provide you the data, right? They will provide you the data, like because they have read so many cases, they will give you some raw data. Okay, so that raw data you have to take, because it is given from the domain expert. So from that data you can apply any technique, and you can say for any new values they have given, you can classify whether he is having some kind of disease or not. Okay, similarly here also, before doing any kind of machine learning algorithm, it is important that you have to collect a proper data set. Okay, that is, you should have a domain knowledge. If you don't have a domain knowledge, you have to consult a person who has a domain knowledge, and you can collect data from him. Okay, and one more question you might be getting, like why we are using this petal length and sepal length as dimensions, as features. Okay, why we are not using color as a feature? Okay, right, because these flowers has color. Why we are not using color as a feature? Why we are using this petal length, sepal length? What are this petal length and sepal length? Okay, so why we are using? Because I mean, you can see only with the help of color, any person can say that you can't distinguish these three flowers, right? With the help of color as a feature. Okay, so definitely there should be some other parameters by which we can classify this flower. So in that direction only, this scientist has thought. So that's why this Ronald Fisher has thought. So that's why he checked this sepal length and petal. So what are sepals and petals is? So you can see this diagram here. So sepals are petals. So this long flower, you can see long leaf. So these long leaves are called as sepals, and the shorter leaves, they are called as petals. Okay. So sepal length means the length, the total length of this leaf is called as the sepal length, and the width means the total width of this leaf is called as the sepal width. Similarly, petal length means total length of this leaf. Petal width means total width of this uh, petal. Okay, so like that I got this sepal length and sepal length, sepal width, petal length, and petal width. Like that, he has collected the data, and he, by his observation after long research, he has calculated the lengths properly, and he noted all the observations, and finally he classified, given this data set. Okay, now, so how to do exploratory analysis on this data set? Okay, we try to do some kind of exploratory data analysis on this data set. Okay, so what is our objective? Can anyone tell me what is the objective? Please don't forget the objective. What is the objective?
To find the flower, iris flower, iris.
Yeah, given these four values, I mean, given these four values like sepal
To
length,
find the
sepal
type
width,
of flower.
yeah, type of the flower you need to find.
Flowers
That is the objective, right?
based
That is
on
the
the four
objective.
parameters.
Yeah, based on these four properties, features, or
Yeah.
four variables, you have to find out whether this flower
Types of
belongs to any one of these
anyone
three
types.
classes.
Yes, sir.
Yeah, any one of these three classes. Okay, so let us see how exploratory data analysis helps this. Okay, helps us for achieving this objective. Okay, now, yeah, so for doing this task, I required some libraries. So I required pandas libraries. Already I discussed about pandas library, right? Because this iris flower data set, again, I have in the form of a CSV file. Okay, so the data set which I have shown to you, this file, this table, I have it in a form of a CSV file. Okay, comma separated file. So in order to load that file, I required panda library, and I'm using here cbun library. So cbun is also used to draw the scatter plots, but in more elegant way. More elegant way means we can draw a color of plots. Okay, with the help of the cbun library, we can able to draw color plots. And this matplotlib, already we know it's used to draw some scatter plots, some other kind of graphical representation. And next, we are using this numpy numerical python to do some kind of numerical operations. Okay, I have provided the github link for this iris csv file. You can click on this and you can download the csv file. I will also share it in your group. You can after this session is over, I will share you the cards dataset. I will share you the iris dataset along with these files, IPython notebook, so that you can run with, say, you can use the code and you can run with some other data sets. You can check with some other things also. Okay, now the first thing is what? First we have to load the iris dataset frame, right? I need to load this iris csv file into my data frame. So already the code is already known, right? So iris is a data frame name. The data frame name I am giving is the iris, and PD is used for pandas. That dot read CSV. So you have to give the path iris.csv. Again, if I run this code, I will get an error, right? Why? Why I will be getting an error?
Because we have not uploaded that file in the Google Colab.
Yes, correct. Yeah, we are not
Without
uploaded the
importing
file in
file in
the
Google Drive. Without
yeah
importing
now
the Google file.
yeah we have not uploaded the file. So file not found error will be coming, right? Because the file is not there. So I have to upload the file. So how to upload the file? Go to this folder, click on this upload button, and that is available on the desktop of my iris dataset. So this is also CSV file. I show you the CSV file, right? They are comma separated file. Same here, the values also in the form of comma separated. So you'll get this reminder message. You just ignore it and you run it again. So I'm printing the file also. See, I'm printing the iris file. So it will give some samples of the data. So you can see it consists of 150 rows and 5 columns, right? So it consists of sepal length, sepal width, petal width, and the species. Okay, species means whether it belongs to Setosa, versicolor, or virginica. Okay, so it has given a sample. It can't print all the 150 rows. It has given some samples of the output. Print iris. Okay, so how many? So what is the size of this data set? It consists of 150 rows. Already I told you, right? 50 observations for each flower classification. So total 150 points are there. Okay, and you can ignore this indices. This indices is given by the data frame. It is of just to show which index is what, which is a first position, second position, like that. Okay, now you can do some kind of operations on this data frame also. So if you want to know this, what is the shape of this data frame, that is you already know 150 rows and 5 columns. You can use this shape. Okay, so iris dot shape means it will give 150 rows. That is the shape of the data frame. So first parameter indicates the rows, second parameter indicates the columns. Okay. Similarly, if you want to know what is the maximum petal width, say this is sepal length, sepal width, petal width, you can do any operation, any numerical operation on this. Okay. If I want to know which row has the maximum sepal length, you can just say if you want petal length or petal width or sepal length, you can write here anything. Okay, and use a function called as max. Okay, so in that column it will give. So here what it is giving the maximum petal width. So maximum petal width I have got it here, what, 2.5. Okay, so you can see all petal widths are like 0 0.2, 0 0.2, 0 0.2 only. So 2.3 is the highest you can see here, but some points are not displayed here. So here it is giving 2.5 highest. So like this you can perform some operations on the data frame. Not only these operations, there are a lot of operations. You just try to see what are the operations you can do with data frame. Okay, you can learn more. Now say if I want to know what are the different columns present in the iris dataset, you just say print iris.columns. When it say print iris.columns, it will print all the columns present in there. So what are the columns I have? I have sepal length, sepal width, petal width, and species, right? These are the 5 columns I have. Okay, now if you want to answer these questions like how many data points for each class are present and how many flowers for each species are present, already these things we know, right? For each class, how many data points are there? 50 data points. And how many flowers for each species? 3 flower, right? Three flowers are there, right? Setosa, virginica, and versicolor. So in order to answer these two questions, you can use this function value underscore count. So you apply this value underscore count function on the total species data frame. Okay, on the species. Then according to the species, so you will get 50 data points on value count. That is 50 data points of Setosa, virginica 50 data points, versicolor 50 data points. Okay, so like this, I told you, not only you can't restrict to only these operations, you can ask so many questions and you can also get so many answers by using this data frame, by applying these numerical operations. Okay, so
Sir,
just
how
for
50
example,
data points?
how to
Sir, how 50 data points has come?
how 50 data points have come
Yes, sir.
here. See what see, this value count is a function, right? This value count is a function I'm applying on the species. So species column is there. So this is a species column. On species column, what I'm applying a function called as value counts. Okay, so what this value count will do is, say setosa is there, right? Setosa in one value, setosa is one value. So it will look for the similar kinds of value. Setosa is value, right? Like this, how many values are there? 1, 2, 3, like that. It will count. There will be a counter automatically count up to 50 points, because setosa has 50 points, right? So it will count 50. Similarly, next value is what? Versicolor. Again 50 it will count. Counter will be there, it will count 50. Again, next what is there? Virginica. 50 points are there. So like that, this value count will count the how many values are there, and it will count. Okay, of types setosa. I done here iris as species, right? So we know that there are 3 species. So for every setosa, 50 points are there. Like that, it is getting. Okay. Now coming to the objective. The objective is what? The objective is to classify these flowers, right? Given a new data set. Okay. Now let us try to draw some simple scatter plot. Okay. I'm trying to draw a simple scatter plot here. Already I have imported these functions, right? These libraries. These libraries, with the help of these libraries, I'm trying to draw a scatter plot. Okay. So I'm applying a plot on the iris data frame. So iris dot plot. I'm saying the kind is scatter. So initially I just give a simple version, right? In the previous session I give a simple version. Here you can see I'm getting the x-axis, y-axis also. How to do that? Just you say the kind is equal to scatter. And on x-axis you want to place sepal length. On y-axis you want to place sepal width. Okay, and you just say simply say plot dot show. Okay, so when you run this code, see you will get a scatter plot like this. Okay, now one observation you have made might be, what out of 4 features, how many features I am considering here?
Features.
How many?
4, sir.
Only 2. Only 2 I am considering, right? Because with the help of scatter plot I can visualize only 2 features, right? Yes or no?
Yes.
Yes, sir.
Yeah, that's why I'm taking only sepal length and sepal width. Not only this, if you want, you can take any other 2 features, any combination of 2 features. Okay, so let us see if with the help of only sepal length and sepal width, can we able to classify these flowers or not? Let us check that. Okay, now as I draw this graph, I mean scatter plot, can you able to differentiate different flowers? Is it easy to differentiate different flowers?
No, sir.
No, right? Because I can see it as a map, a world map, where all points are in same color. I can't figure out which points belongs to which flower, right? It is very difficult. Okay, so what if I color these dots? That means how I will color it. So I know that we have 50 points of setosa, and I know that we have 50 points of virginica, and we know 50 points of versicolor are there, right? Okay, so for every these points, what I will do is I will give a separate color. Okay, so how to if I give a separate color, the graph will be like this. See, I will explain you the code how I draw this. Don't worry. See the graph. Now you can see the blue points belongs to setosa. Okay, this orange points belongs to versicolor, and this green points belong to virginica. Okay, the species, the legend is given here. Okay, now can you able to classify any of these flowers from other flowers by seeing this graph?
Yes, sir.
See this,
Yes, sir.
see this graph, and tell me whether can you able to classify any of the flowers from other flowers. Which flowers are classified from other flowers?
Setosa.
Yeah, setos are classified from other flowers, right? That means if you draw a linear separable line like this, a straight line here, you just imagine a straight line on the movement of my cursor, because I can't annotate here. So on the movement of my cursor, if I draw a straight line here, the points on the top of the straight line are the blue points. That is, setosa flowers can be easily classified with the versicolor and the virginica points. Yes or no?
Yes, sir.
Yes.
Yeah, yes. Okay, that we can do. Can we able to classify these 2 points, the orange points and green points? Are they linearly separable?
No.
No, sir.
No, sir.
No, sir.
No. Only blue points, I mean, the setosa flower points are linearly separable from the rest of the flowers. But this versicolor and virginica points are not linearly separable. I mean, I can't draw a line such that I can classify these two flowers. Okay. But here, see, I have considered only two features, right? Sepal length and sepal width. Okay. We can try with other features also. Okay. We can try with other features. Now, yeah, let us see the code, how I draw this, how I got this color chart. Okay, the code is very simple. You can see here. So for this, I have to use this Cborn library which I have imported. So I told you, right, the Cborn library is used to draw color plots. Okay, so I imported this Cborn library as SNS. Okay, so you can see here I'm using the same Cborn library to draw this plot, to draw this to color plot. Okay, so this 2D scatter plot with color coding for each flower type and class. Here SNS corresponding to the Cborn. Okay, so SNS I'm using is nothing but it corresponds to the Cborn. Okay, so look at the first code, first line of the code, SNR dot set style wide grid. So what it will do is it will construct the background wide grid. So there is a if just consider there are no points, then it will, what it will do, just it will draw a wide grid. So it will set up the wide grid. So the first line of code will set up the wide grid. Okay. Now the second line of code, what you want to draw on that wide grid, that we call it as a phase grid. Okay. So I want to draw what? I want to draw all the points of iris flower. Okay, and I want to color it, right? I want to color it according to the species, right? So when I say hue is equal to species, then according to the species, the points will be colored. So hue indicates actually color. Okay, so hue, HUE, hue indicates what? Color. Okay, and the size is equal to 5 indicates the size of the chart. Okay, if you want a bigger chart, you can increase the size to 6, 7 or your wish. Okay, and upon this phase grid, what I am plotting? I am plotting a scatter plot with the sepal length on the x-axis, right? Sepal length on the x-axis and sepal width on the y-axis. Sepal width on the y-axis. Okay, I'm mapping it to the phase grid and drawing a scatter plot. Okay, and when I say add dot legend, add underscore legend, so this add underscore legend gives this thing, the
So what?
species. That was a
Dasya
vertical.
the
Please mute yourself. Please mute yourself. Hello. So the species setosa versicolor verticolor. So when I say add underscore legend, it will give this thing. Okay. I hope you understood the code. The code is very simple. The first line of the code is for the wide grid, I mean background. The phase grid is for the phase ground. I mean what you want to put it. I want to put a species according to the color, and this is a size. And there I'm drawing a scatter plot by taking the x-axis on the sepal length on the x-axis, sepal width on the y-axis, and this legend indicates this. Okay, so this is the code for drawing this color plot. Okay, now what are the observations we made from this color plot? We made that the sepal length and sepal width, by using these features, we can say that we can distinguish the setosa flowers from other flowers, right? Setosa flowers means these blue dot flowers. Okay, these blue dot flowers are separated from the rest of the flower. That is, setosa flowers are separated from the rest of the flowers if we consider sepal length and sepal width as the features. Okay, by drawing only 2D scatter plot. Okay, so if can we able to separate these two, versicolor and virginica? We can't. Okay, so that is the two observations. It is very hard to separate because there is a overlap between these 2 points, so it is very hard to separate these 2 points. Okay, now what if I add one more feature? So here I consider only 2 features, right? So let us say if I consider one more feature, can we able to classify the points? Let's see. So that is, we call it as a 3D plots. So if you visualize the 3D plots, it will be like this. So they have drawn a 3D plots in plot. There is a library which have drawn this 3D plots in different ways. You can just after the session is over, you can check this with this code. So here they are taken sepal length, sepal width, and along with the petal width. They have considered three features. And you can see this is the graph. By the movement of my mouse, the graph will be increasing and decreasing. So I'm just scrolling my mouse. So see the points are coming. It's very sensitive. Yeah. and with the movements of the mouse I can rotate. Here also if you observe, see a lot of these points are overlapped here, right? Only the setosa points are well separated. Okay, even though I consider another feature, again the points are overlapped here. I can't draw a hyperplane to, I can draw a hyperplane to separate these blue flowers from the rest of the flowers, but I can't draw a hyperplane to separate these green dots from the red dots. Okay, that is versicolor from the virginica. Okay, so what, so you can see there are different ways they have drawn. They have taken different, I mean, uh, they have taken diamond for sepal length, circles for sepal width, like that, and squares for sepal width. So like that, I mean, I told you now you can write any code. The code is here. You can see the code also. Okay. So what I mean to say is, even though if I consider 3D plots also, 3D scatter plots also, okay, I can't able to properly classify. Okay. Now what about the 4D plots? So can you visualize 4D plots? Is it possible to visualize 4D? We human beings can only able to visualize 3D, right? We can't, we are not trained to visualize 4D. Okay, only we think in the terms of length, width, height only, right? Only in 3 direction we can see. The fourth dimension we can't see, right? So but how to visualize all dimensions at one time? Okay, so to visualize all dimensions at the same time, we'll be using pair plot. Sorry. So in order to visualize the 4D dimensions, we can able to do with, just give me one minute, 1 second. Sorry for interruption. Yeah. Now, what I was talking, yeah, can we able to visualize the 4D plots? We can't directly visualize the 4D plots, but there is a way by which we can try to visualize all these 4 features at a time. So that plot we call it as the pair plot. Okay. So pair plot, what it will do is, it is a pairwise scatter plot. Okay. You can see, for example, yeah. So so how many features I have? 4 features, right? Sepal length, sepal width, petal length, petal width. Okay. If I take 2 features at a time, how many plots I can draw? Pair plots. Pair means 2 features at a time, right? Pair plots. Okay. How many pair plots I can draw? Can anyone tell me? Hello?
2.
2?
8.
8?
8, sir.
8. Oh, see, I have 4 features. If I
6.
take,
16.
two,
6 features.
if
6.
I take 2 features at a time, so how many combinations I will get? 4C2, right? So 4C2 means how much?
6.
Yeah, 6. So that means 6 pair plots I can draw, right? So what are those 6 pair plots? Sepal length, sepal width, sepal length, petal length, sepal length, petal width. Next, sepal width, petal length, sepal width, petal width, and petal length and petal. So what if I can able to visualize these pair plots at one place, like in a form of a matrix, like in a form of a matrix, if I able to visualize this 6 plots, 1, 2, 3, 4, 5, 6, like this at the same time, then it's as good as visualizing 4D plots, right? Not exactly, but I mean, we can able to, we are trying to see all the features at the same time or not? Yes or no? So with the help of pair plots, we can say that we can indirectly visualize 4D, but in terms of 2D plots, but more number of plots will be there. Okay, so you might be getting doubt like sepal length, sepal width, sepal length, both are same only. Okay, so this is x-axis, this is y-axis. When sepal width comes first, then it will become y-axis, it will become x-axis. Okay, so I mean they are symmetric, so I'm not considering this reverse conditions. If you consider the other condition, you will get 12 plots. Okay, but I want unique combinations, right? So we'll get six combinations. Okay, now let us see how to draw these pair plots. Okay, we'll try to draw the plate plots and try to see what we can dig out of it. Okay, yeah. Now come here to the code. So for drawing the pair plots, the code is very simple. So already this thing we know, right? You just set the style of the white grid. You set style as white grid, and there is a function called as pair plot, which is available in SNS. With SNS, you just say pair plot. Only you have to use this keyword. And on which data set you are drawing pair plot? You are drawing pair plot on the iris data set. Okay, and the color, you want to give color to the species, so I want to give 3 colors. I mean 3 species, there are 3 species, so automatically 3 colors will be given, and I'm saying the size of the pair plot is 3. And when I say plot dot show, it will show the plot. And please see the plot now. This is a pair plot I have drawn, and you might have so many questions now, right? So what are these graphs? Okay, so right now this pair plot is drawn in this way. I mean, I will tell you how it is drawn actually. So actually, it is drawn in a form of a 4 cross 4 matrix. Okay, so 4 matrix means 16 elements, right? Because there are 4 features, 4 cross 4 matrix, 16 elements it has there. So how it is drawn is like this. Consider yeah, 16 elements are there, right? Now it is drawn like this. Say this is sepal length, this total row is sepal length, this is sepal width, this is petal length, this is petal width. Similarly, you consider this as sepal length, sepal width, petal length. Oh, I require one more. Petal width. Okay. So in this, we required only 6, right? 4C6, 4C3, 4C2 means what? 6 combinations are required. Okay. So you can consider any of this combination. I mean, you can you ignore the diagonal elements. You just ignore the diagonal elements. Okay. Either you can consider the upper triangular matrix, or you can consider the lower triangular matrix. So if you ignore the diagonal elements, if you see the upper triangular matrix contains only 6 elements, 1, 2, 3, 4, 5, 6. Similarly, lower triangular matrix also you will have 6 elements. This also, right? Are you getting the point? So in that way, that the graph is drawn here. Okay, you can see sepal length. This total row is sepal length. This total row is sepal width. This total row is petal length. This total row is petal width. And this total column is sepal length. This total column is sepal width, petal length, petal width. Okay, and what are these diagonal graphs? I will talk about it. They are normally called as PDFs, probability density functions. I talk about it in some while. Okay, now you consider the upper triangular matrix. I mean these graphs, this pair plot, this pair plot, this one, this one, this one, and this one. So the 6 combinations we got. Okay, everyone following or not? Or is my voice
Yes,
audible?
sir. Yes, sir. Yes, sir.
Okay, thank you. Right. Now, if I take this first graph, so it is drawn between sepal length on the y-axis, on what is on the x-axis? Sepal width. Okay, this graph. Now, if you see this graph, sepal length and sepal width on the x-axis and sepal length on the y-axis, so you can see the blue points are okay, linearly separable, but there is a lot of overlap between the green points and the orange points. So these 2 points cannot be linearly separable. Yes or no? Now you look for the much better graph. You see the second graph. The second graph is much better than the first graph, right? Which is drawn between the sepal length and petal length. Okay, so here you can see the blue points are very much linearly separable. Yes or no? And orange and green points are okay, they are separable, but not that much. So like this, if you look at each and every graph, you come to this graph. Okay, you come to this graph, which is drawn between petal length on the y-axis and petal width on the x-axis. Okay, you see this graph, I just put it here, the same graph, so that we can do some kind of analysis here. So you can check this. So blue dots are here, you can see. I'm not drawing exactly, but just think of like this. The blue dots are here. You can check. The blue dots are here, well separated, and orange and green dots are here. So red. So you can think this as orange dots. And you can think this green dots, right? So green dots are somewhat overlapped. So green dots are somewhat overlapped here. Not totally, some overlap is there. Okay, and you see the, if you see the scale here, you can see the scale. It is starting from 1, 2, 3, 4, 5. Yes or no? The scale of the y-axis is 1, 2, 3, 4, 5. Similarly, you can see the scale of the y-axis is what? X-axis is 0, 1, 2, 3. Okay, so if I do it, same thing here. So this is 0, 1, 2, 3, 4. Similarly, here also we can call it as 1, 2, 3, 4, 5, 6, 7. Okay, now look, now I try to draw the graph here, not exactly, but try to see. So you can, what I want to say is, now look at this graph. Now these points are well separated, right? I mean, the say blue points are well separated from the red and the green points. Okay, now can you write here, can you write a simple if else rule, if else rules, so that you can, I mean, you try to build a model by writing a simple rules like if else rules, which can separate these flowers. And what is the x-axis? X-axis is what? Petal width. X-axis is petal width. Y-axis is petal length. Yeah, can anyone write a rule? Simple rule here. How can I write a rule?
Sir, if x less, sir, can I speak?
Yeah, speak, please.
Sir, if x less than equal to 1 and y.
What is x means? What is x means?
Petal width.
Petal width. Yeah, if petal width is less than 1
and y petal length.
Petal length is less than
1.
1 or 2. Say this is 2.
Okay, 2 is written. Okay, 2.
2. Then I classify this flower as setosa.
Yes, sir.
Okay. Yes or no? Similarly, here also, if you draw a boundary like this, I mean, not exactly, but some points are overlapping. 100% accurately, we can't classify. You just try to draw a boundary like this. Okay. And for this also, can I write a rule like this? Same rule. And for this also, can I write a same rule like this if I'm drawing the boundaries with the help of the petal width and petal length? Okay.
Yes, sir.
So that means, yeah, that means what? If we try to visualize the data in this way, in pair plots, you can see we will get some combination of the pair plot where we can able to build our own models, simple rule-based model by which we can classify the flowers. Okay. So that is what I want to show you with the help of these pair plots. Okay. Now the question is, what could be the disadvantage of this pair plot? Can anyone tell me what could be the disadvantage of this pair plot? Uh, what could be the disadvantage of pair plot?
If there is no proper separation, if we can't see
No.
separation between the points, then it is difficult for us to write a rule-based condition, right?
Yeah, I mean, at least we got some this features, right? Petal width and petal length. If you consider here, 100%, okay, we can't got the rules, but okay, at least with the help of petal width and petal length, we can able to write some rules, right? Okay, that is one advantage only. The major disadvantage is, see how many features we have. 4 features, right?
4 features.
But 4 features, how many pair plots is possible?
6.
Say if you have 100 features, so many pair plots are possible, right? Yes or no? Very big number of pair plots
Right.
will be possible. Yeah, so in that case, I can't able to analyze all the pair plots, right? It is very difficult to analyze each and every pair plot. Okay, so when the feature size, I mean the number of features is, if it is less than or equal to 4 or 5, then in that case only we can go with the pair plots. Okay, but if the feature size is high, I mean the number of dimensions is high, the dimensions increases, the number of pair plots is also increases, and it is very difficult to analyze each and every pair plot. So that is the major disadvantage of the pair plot. Okay, so what are the observations we made in this graph? The major observation is, which from out of all these 6 features, which feature is better now? Out of all the 6 features, which features are better? Petal length and petal width. These two are the most useful features to identify various flowers. But Setosa, these blue points are very much linearly separable. But this Virginica and Virginica, there is some overlap. So we can call them as almost linearly separable. Okay, and we can find this simple if else conditions. We can write simple rule conditions to build a simple model to classify these flowers. Okay, so okay, now see, till now we were talking about 2D plots. We have talked about 3D plots, and we also talked about 4D plots with the help of pair plot. Okay, so what about the 1D plot? Can we able to visualize 1D plots also? Yes, answer is yes. We can also able to visualize the 1D plots. Okay, so 1D plot means only you can visualize for sepal length, only you can visualize for sepal width, taking only one feature at a time. Okay, only you can visualize for petal length, only you can visualize for petal width. Okay, you can take single feature at a time and you can able to visualize. Okay, let us see how to do that, and what are the disadvantage of this 1D plot, and what are the ways by which you can more precisely you can draw this 1D plots. Okay, let us see these two things now. Okay, so let's see now. Yeah, I will show you the code. Before going to the code, just see this diagram. Okay, so this diagram is drawn with only by taking only petal length. Okay, by taking only petal length of all the 3 flowers. Okay, and you can see on the y-axis, the y-axis I have taken y-axis as 0. You can see on the 0 line there all points are drawn. So I'm considering only sepal length as the feature, any one feature. So in this case I am considering petal length as the single feature. Okay, now when if I so what could be the problem if I draw a single dimensional plot like this? The problem could be, see, if the points are well separated, then there won't be a problem. But see, this point is well separated. I mean, this is independent. This orange point here is independent. This is also independent. I can see here 2 points. I can see here 2 points. But here there are so many overlaps, right? So if I want to know how many points are here at this location, it is very difficult to tell, right? With the help of only single dimension. Okay, with the help of single dimensions, it is very difficult to say. For example, I will explain it more clearly here. For example, I have taken this graph here. So this is 0, 0.0, that is on the y-axis. Okay, on the x-axis, I am drawing the petal length. I am considering the petal length on the x-axis, and you can see some blue dots are like this. like this. Some are overlapped, some are separated like this. In the orange and this also you can see some are overlapped, some green points are overlapped with orange points, some green points are overlapped with orange points like this. Okay. Please mute yourself. Hello, someone has unmuted. Please mute yourself. Yeah. Okay. Now, if you see this graph, same graph I'm trying to mimic here. So I can't say if there is overlap. I can't say how many number of points are there with sepal length, petal length or sepal length. Okay. Here also how many number of points are there with sepal length. Okay. So in order to overcome this problem, what if say the x-axis is what here? You can see the x-axis is what? 1, 2. These are petal length, right? 1, 2. If the petal length 1, petal length 2, petal length 3, petal length 4, petal length 5, petal length 6, 7, like that, right? So what if I divide this petal lengths into some bins? Say 1 to 2, like 1.2, 1.4. So 5 bins like this: 1.6, 1.8. Similarly, 2.2, 2.4, 2.6, 2.8, and 3. So like this, if I divide it into bins, okay. Now you draw another graph here in the same way. Here you'll take the petal length, and these are the, this is 0. Sorry, you can call it as 1 or 0. 0.2, 0.4, 0.6, 0.8, and 1. So these are 5 bins. Again 1.2, 1.4, 1.6, 1.8, 2.0, 5 bins. Like that, you divide all the intervals into 5 bins. Okay. Now on the y-axis, you put a count. Okay, you put a count. That means from 0 to 0.2 length, say you can call this count as some number. You can give some scale to this count also, say 2, 4, 6, 8, 10, 12, 14, 16, like this. Okay. So if I say from 0 to 0.2, say there are two flowers with whose length is between 0 to 0.2. Say from 0.2 to 0.4, say there are some 8 flowers whose petal length is between 0.2 to 0.4. Okay. Similarly, some number of flowers for 0.6, some number of flowers for 0.8, some number of flowers for 0.1. Okay. Now, if I able to connect this in the form of towers like this, if I able to draw a towers upon like this, okay, these towers are called as what? Histograms. So histograms are the more precise way of showing, uh, uh, visualizing the single dimensional feature. Okay, so histograms are more precise way of visualizing the single dimensional feature. Here in this case, petal bin. Okay, so now you can see, right? So 0 to 0.2, how many are there? 2. I can see with the, while seeing that histogram, I can find out how many count. I can find out the count. How many number of flowers are there whose length is between in this interval. Okay. Instead of drawing this graph, if I draw histogram, it is more precise way of designing a single dimensional feature. Okay. So let us see how to draw those histogram. Yeah, before that, so how to draw this? It is very simple. I have collecting all the iris setosa, virginica, and versicolor data frames, and upon species, okay, I'm collecting setosa, virginica, and versicolor, and I'm only considering the petal length. So I'm considering the petal length on the x-axis, and I'm saying the zeros on the petal length of the zeros on the y-axis. So on x-axis, I'm considering petal length, and y-axis I'm considering zeros. So that's how this graph is drawn. Okay. Now in order to draw the histograms, so you just say SNS phase grid is equal to species. Okay, and you have to use a function called as a distribution plot. Okay, so the distribution plots gives us the histograms. Okay, the distribution plot gives us the histograms on the single dimension petal length. Okay, so when you see the graph will be like this. See, the graph will be like this. You might be asking, sir, what is this? What is this graph, this curve, this mountains? Okay, I'll talk about it. So this, yeah, these mountains, these curves are nothing but a smoother form of histograms. So if I smooth the histograms by taking the edges like this, say I'm taking the edges, I'm smoothing it. Okay, then it is called as a probability density function. Smoother form of a histogram, smoother form of a histogram is called probability density function. Okay, so why this probability density graphs are used? I will tell you. What are the importance of this probability density graphs? I will tell you. Okay, now if you see this graph, so these are the histograms for the setosa flower. So these tall towers, you can see, these are the histograms. You can see at this point of time, say this is 1.5, right? So 1.5 length flowers, so many flowers are there. So this is the density, that is 30% of the flowers are 1.5 of length. Okay, so if you smooth this histogram, you will get a probability density function, probability density curve. This is for the versicolor, this is for the virginica. Okay, similarly here also, if you try to write a rule, if simple if else rule, can anyone write a rule here by seeing this graph? Yes, can anyone unmute and tell me the rule by which we can separate these flowers, setosa flowers, from our remaining flowers?
We can, based on the
The
density,
length is less than 2.
based on the
Yeah,
density, we can make
yeah,
it.
yeah. If the petal length is less than 2, then I call it as a setosa. Okay, so what if I want to do a separation between these two? So there is considerable overlap here, right, between this versicolor and virginica. So how to write a proper rule here so that I can classify some flowers as versicolor and virginica? So normally a rule you will be writing like if the petal length is greater than 2 and less than 6, right? Less than 5.8. Normally how we will write?
So petal length is between 2 and 4.8.
2 and
4.8.
4.8.
Yeah,
4.8.
approximately.
Why you are considering 4.8?
And because it's lying between 4 and the 5, right? So you can take it 5 maybe.
5.
The intersection.
Yeah, intersection. Yeah. By the gut feeling of intersection, you have taken this as 4.8, right?
Yeah.
Okay. Yeah. If I take, yeah, now I will tell you the importance of the probability density function. Okay. So if I take the intersection of this point, these 2 points, what is the intersection of this 2 points? If you draw a perpendicular here, it will be say 4.8, right? This point.
Yes, sir.
Yeah, 4.8. Now, for example, suppose if I got a flower whose petal length is 4.5. Okay, if I got a flower whose petal length is 4.5, so in which way you will classify it? You will, whether you will classify it as a versicolor or virginica?
Versicolor.
Versicolor.
Versicolor. So how, why you are classifying it as versicolor? So because if you draw a perpendicular, I mean, you can see the towers here. Now you see these mountains. Okay, this mountain gives you what? High probability of that flower being versicolor. This low thing means what? Low probability of that flower being virginica. Similarly, if you get a flower whose petal length is 5.5, 5.1, in that case also you can see you will classify it as virginica. Why? Because you can see this tower. I mean this probability. This probability density function gives you what? The probability of that flower being virginica. Okay. So the probability density functions are useful in that way. So whenever there is a overlap, you just take the intersection point, okay, and which are the points coming in this direction, you check these curves. Which are the curves having the highest probability, you classify the flower into that flower. And similarly, which are the points coming in this direction, again you see these two curves, and which are the flowers having the highest probability, you classify that flowers into that classification. Are you getting the point?
Yes, sir.
Okay. Now, similarly, this is for petal length, right? Okay. Now we have other 4 features also: petal width, sepal length, sepal width, petal length, petal width, sepal length, and sepal width. Okay. So we are drawn for petal length. Let us draw the same probability density function for petal width also. Okay, so it's the same code. I'm just changing the feature as petal width. Okay, so when I draw this, you can see the diagram here. So this diagram also you can see it's similar to this diagram only. Here also the blue points are well separated from the remaining points, and you can take this intersection point and you can call. Okay, and now let us see what if I draw for sepal length. See, when I draw for only sepal length, there is lot of overlap between all the points. Yes or no?
Yes, sir. It's hard to classify.
Yeah, very difficult to classify. Similarly, if you see only for sepal width, it is very worse, right? Even worse than this.
Yeah, it's even harder.
Yeah, he's very even harder. Okay, so when we this is a univariate analysis. That means what? Univariate means what? I am taking only one variable, either sepal length, sepal width, petal length, and petal width, and I'm trying to classify these three flowers by drawing PDFs and histograms, right? Now, out of these four features, can you tell me which features you will pick up now to classify these three flowers?
So petal length.
Yeah, petal length will be the first priority you will be giving. Second priority you may give to petal width, and you will ignore these two features, right? These are not good features to classify for doing univariate analysis to classify the three flowers. Okay.
Yes, sir.
Oh, yeah. Now let us look into now CDFs. So we discussed about PDFs, right? Now let us discuss about CDFs. So CDFs means cumulative distributive functions. Cumulative distributive functions. Okay. So with the help of PDFs, we can able to draw CDFs. Okay. So what is the importance of CDFs? Let us see. First, you see the graph. Then we'll discuss about the. You try to see one graph here. It is drawn between petal length. Okay, you take this graph. Okay, the blue line here, it is drawn only with the setosa flower, I think. Okay, I will show the code. This blue line here indicates the PDF. Okay, the blue line indicates the PDF, and this orange line indicates the CDF. Okay, so cumulative distribution function. Okay, better I will draw here so that you can easily understand it. This is the line. So if I'm considering the only petal length as feature, okay, say this is petal length 0, 1, 2, 3, 4, 5, 6, say 7, maximum say 7 is there, and you consider this is the density. So yeah, I'm considering, so the values are between 0 to 1 here in cumulative. So I'm considering as 0, 0.1, 0.2, 0.3, so on. I say 0.4, 0.5, 6, 7, 8, 9, and 1.0. Okay. Now let us try to draw a normal PDF by looking at this. So randomly I'm drawing. It's not exactly correct. Say this is the PDF for, this is PDF. Probability density function for petal length of say setosa flower. I'm drawing only for one flower, setosa. Okay. Now similarly, I'm drawing another curve like this. Okay, and I call it as CDF, cumulative distributive function. Okay, so what is cumulative distribution function is? Say for example, if I want to know, say if I draw a simple, say if I draw a perpendicular from this point, some 6. Okay, and if I draw a perpendicular in this way, okay, so what is the value you are getting? Says assume it is say 0.95. Yes or no? Okay, so what this is telling is there are 95, how to write this in English is, there are 95% of flowers, there are 95% of flowers of type setosa, whose petal length is less than 6. Whose petal length is less than 6. Are getting the point? What CDF is giving? Similarly, if you write from 4 to here, if you draw a perpendicular, you can see, so it will get nearly 0.55. That means what? There are 55% of flowers whose petal length is less than 4. Obviously, if you draw for the last one here, this last one, that is say 6.5 is the highest. So you will getting what? There are 100% of flowers whose petal length is less than 6.5. That will be always true, right? So cumulative distribution function, it is giving this information. Is this information is given by PDF? No, right? So this kind of information is given only by the cumulative distribution function. Okay. If you want to check how much, I mean, cumulatively it is telling how much percentage of flowers are there whose petal length is less than 6. If you consider only petal length, it is petal length. If you consider petal width, you can consider petal width. So any single dimensional feature you can consider. Are you getting the point here? So you can see here if you say 5.8, so 100% of the flowers are there whose petal length is less than 5.8. If you take this 100%, you can draw a perpendicular here. 81% of flowers are there whose length is 5.4. Now, how to draw these cumulative distributive functions? Okay.
Sir, your screen is not visible.
Screen is not visible?
No, it's visible.
Sir, it's visible.
Screen is visible.
It's visible, sir.
It's clearly visible.
It's visible, no? Okay, okay.
Yes.
Can you see? Can't you see my whiteboard?
Yes, sir.
It is fine
we
now.
can
It is
see
fine
it.
now, sir. Thank you.
Okay, fine. Okay, right.
So maybe his network issue.
Yeah, maybe, yeah. Now, you understood what is the importance of CDF? What CDF is giving?
No, sir, not exactly.
So CDF tells you, see, I draw this, right? So if I draw if I take any point here on the x-axis, and if you draw a perpendicular to the CDF, and if you get the value of y here, so you are getting 95%, right? 0.95 means you can call it as 95%. So 95% of the flowers are there in the setosa flower, setosa flowers are having whose petal length is less than 6. Okay, so this information is given by the CDF. Okay, now so if I draw a CDF, okay, one more important point I forgot to mention is, yeah, I will take a new book here. So I will draw a CDF and PDF once again. So how to get this PDFs? Yeah, the people who are not understand CDFs, you can understand now better. So this is PDF, and consider this as the CDF, corresponding CDF. Okay. So you can, sorry. Okay. Now, so you consider this as PDF and consider this as CDF. Okay. So how we can construct this CDF from PDF is, we already know that the PDFs are nothing but these intervals, right? They are made from towers, these towers only, right?
Sir, are we successively adding the values of the PDF to get the
Yes,
CDF?
yes. Correct. That is what I'm going to tell. We are cumulative. Cumulative means what? Cumulative sum means what? We are successfully adding the previous values. Okay. For example, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7, this is 8. So these are all the petal length. So 1 indicates what? So what PDF will give? PDF will give how many count, right? So there are 2 flowers whose PDF is length 1. There are 4 flowers whose PDF is length 4. There are 4 flowers whose PDF whose length is 3. Okay. there are some number of flowers whose petal length is 4. So like that we are getting, right? Now if I want to find out at particular point here on the CDF, it is nothing but what? You have to add this, cumulatively add this, add this, add this, add this, add this, then you will get a point here, graph. That is nothing but the CDF. Okay.
That's why it never comes down, the CDF.
Yeah, CDF will never comes down because it is a cumulative distributive function. Okay, and it is also found by taking the area under the total area under this PDF is nothing but CDF. The total area present under this curve, that is PDF curve, that is nothing but your CDF. Or we can also call integration of PDF in mathematical terms. If you integrate PDF, you will get CDF, and if you differentiate CDF, you will get PDF. Okay, so cumulative distribution function means what? Just if you successfully add all these things, okay, of previous length, you will get a CDF curve. Okay, so
Sir,
how to
please
draw this
repeat
curve?
to get the CDF.
Sorry,
Sir,
please.
repeat what we have to add to get the CDF from this diagram.
Okay, I will repeat again. You know what is PDF, right?
Yes, sir.
So this is PDF, right? How we got the PDF? PDFs are nothing but smoothed histograms are not.
Yes, sir.
So from histograph only we got PDF, right?
Yes, sir.
So these are all the histograms. If you smooth it, you will get the PDF. So these are all nothing but the values, length of the petal length. Say these are petal length of a flower. So 1 is the first petal length, 2 is the petal length, 3 petal length, 4, 5, 6. So what this histogram is giving here? Say if this is 2, what it is giving? There are 2 flowers whose petal length is 1. What this histogram is giving? Say this is 4. There are 4 flowers whose histogram is, whose petal length is 2. Are you getting the point? What PDF is?
Yes, sir.
What CDF is? CDF is nothing but, if this is CDF, okay, at this point of time the CDF value will be what? Addition of this and this will be this. At this point of time, addition of this and this will be this. At this point of time, addition of this will be this. Okay, at the last point, addition of all these bars is nothing but CDF.
Okay, sir.
So what CDF is giving is, okay, for example, say for CDF curve, it will lie between 0 to 1. Okay, so at say at this point, say this is 6. Okay, so petal length is 6. If I draw a curve like this, if I draw a perpendicular like this, say it is nearly say 60% or 0.6. So what CDF will tell is there are 60% of flowers. There are 60% of flowers whose petal length is less than 6. In total 50 points, we have 50 points, right? In every data set. Okay, 60% of 50 means how much? 30.
30.
So there are 30 flowers whose petal length is less than 6. So this information is given by the CDF. Obviously, if you take the last point, okay, so it will be always 100. 1 means 100, right? So obviously, all points here less than will be, there are 100% of the points are less than the last point, right? Last petal length. Are getting the point? So this information is given by the CDF, cumulative distributive function. Okay. So how cumulative distributive functions are used again? So you can see I have drawn the cumulative distributive functions for the setosa flower, PDF and CDF of setosa flower, PDF and CDF of the virginica, PDF and CDF of the versicolor. Okay, and these points are easily classified, right? Because you can see if your petal length is less than 2, these are classified. Okay, the problem comes when you're classifying these 2 flowers. Okay, so as we said, as we check in the PDF, you can take the intersection point. Okay, and if you take the intersection point here, okay, and say intersection point is 5, for example. Now if you draw a perpendicular onto the CDF of this flower, what is the value, corresponding value here? Are you getting the point? Just follow this mouse curve. So phi, this is the intersection point, okay? And you draw a perpendicular onto the CDF. And what is the corresponding Y value for this?
95.
Say 95%, right? So that means what?
Yes.
Yeah. So what it is telling is 95% of the time, it will classify the flower as Virginica. If this is Virginica, it will classify flower 95% of the time it will be true. Only 5% of the time it will be misclassify. Are you getting the point? That is the importance of CDF. So it will tell us how much, by how much chance the flower will be Virginica or versicolor. Here in this case, this is you consider this flower as Virginica. So if you take this intersection value, the value corresponding will be what? Say 95. So you can say that 95% of the time the flower will be classified as Virginica. That is correct classification. Only 5% of the time it will give a wrong classification. Okay. So that is the way you have to look at the CDFs. Okay. For drawing the CDF, just only this function is used. Come sum, remaining things are same. You have to use this cumulative sum. So cumulative sum of PDF is nothing but the CDF. Okay. So that's all I want to discuss with you. Yeah, if you have any questions, you can ask me, and I will share you these files with you to the organizers. They will share it with you, and you can run the code. You can change your data set. You can try with your own data set. You can change the values and see, and you just explore more. Then only you can learn more. Okay. Yeah. Any questions? I will take some questions and
So
we'll.
do we need the PDFs if we have the CDF?
See, PDFs are generated from the CDFs are generated from the PDFs only, right? I mean, there are, see, what information CDF is giving, that information is not given by the PDF. PDF will not say, but how much accuracy I can classify this flower as that flower only. But CDF is giving that information, right? In CDF, it is giving that 95% of the time the flower is classified as that flower only. Only 5% of the time it is giving mistake. That information will not be given by the PDF. So PDF and CDFs are, they are like they're mutual. They are required. PDF has its importance and CDF has its own importance. If you're able to classify with the help of PDFs, that's okay. No, then you can check with you draw the CDF curve also. Then you can try to classify your data set like that.
Yeah, so it's a much better classification when we have both.
Yeah. Yeah. Any other questions?
So how can we PDF and CDF in the same graph, because both of them are giving different information. Like PDF is number of count and CDF is percentage. So like how can we interpret that?
Yeah. No. Yeah, actually, yeah. For drawing both things in the same graph, we already when I draw this graph, it is respect to the CDF, because already for this graph we know that is the only count. Okay, so if you draw the boxes here and you count, that is scaled as here 0 to 1. The cumulative distribution function is scaled between 0 to 1. So for that the code is given here. You can check this code. Okay, for that we will be dividing it into 10 bins. I mean, we divided, right, 10 bins. We have dividing it into 10 bins, and we have to check the this edges also, bin edges also. Okay, and how many number of PDFs are there, you have to do some count. So this is the code by which you can transform this scale also. Okay, just go through this code, then you will able to understand it. Yeah. Yeah, any other question?
So like the speed with which the CDF is rising, does it tell us something?
What? Come again?
So like some of the CDFs, they have like a very sharp slope. They're going up very quickly, and some are like they're going up much slowly, like this one. Yeah. So does it tell us something? Like the orange
Yeah, I mean,
CDF, it's going up really quickly, while the red one is a
okay.
bit slower.
Yeah, they are saying the same thing. I mean, by what percentage? I mean, it will give the chances of being that flower as that flower. Okay, So I mean, these curves are according to the PDFs only. They are drawn according to the PDFs only. These curves are drawn.
Okay, okay, sir. I understand. Yeah.
Mhm. Yeah. Any other
Uh,
questions?
okay, sir. I think that is it.
Yeah. Thank you. Yeah.
So
Thank you very much. Yeah.
regarding the PDF, CDF, you just go and check frequency and cumulative frequency. Okay, see
Yes.
the OJIF. Go and look for it. You'll understand this better. So it's from my side, and I think it is. That is it. We are going to conclude our session for today.
Yes. Yes. Sir. Thank you, sir. Thank you very much for giving me
And
this
sir,
opportunity.
are you going to take tomorrow's sessions as well, or should I contact Raju sir?
No, sir. I may not be taking tomorrow's session. Just contact
Okay,
once
sir.
Raju.
Okay, sir.
Some other resource
Okay,
person may come.